Begin with a number that is hard to hold in the mind. 252 million years ago, every scrap of dry land on Earth was fused into one body. There was a single continent then, and it wore the rough shape of a thickened letter C, its long arms curling around a warm central sea. Geologists gave that continent a name long after it was gone. They called it Pangea. Around it stretched one ocean so vast it swallowed most of the globe, a body of water called Panthalassa, wider than any sea that has existed since. Stand anywhere on that supercontinent and the nearest coast could lie 1,000 miles away. You are there now, in the last long afternoon of the Permian period. Let the number settle. One landmass, one ocean. A world simpler in its geography than any you have known, and far stranger in its life. If a slow walk through deep time is the thing that loosens your shoulders at the end of a day, then stay a while. There is nowhere to be. Let the voice do the walking, and let the ancient heat do the rest. The interior of Pangea is a hard place to make a living. Because so much land sits so far from the moderating breath of any coastline, the seasons swing to violent extremes. Summers bake. The ground cracks into wide polygons, and the air over the flats shimmers the way it does above a stone left too long in the sun. Winters, in the same interior, can turn cold enough to touch the puddles with frost at dawn. There is little coastal moisture to soften the swing, so the land lurches from oven to chill and back again across the turning year. A creature born in the deep interior lives its whole life inside that pendulum. Walk out onto one of those dry basins at midday and the dust rises around your ankles. It is fine as spilled flour, pale and weightless, and it settles into every crease and seam. The heat presses on your skin like an oven door held open a few inches from your face, steady, patient, unbothered by whether anything can bear it. Nothing hurries here at noon. The animals that can dig have already gone underground. The ones that cannot lie in whatever shade the low plants offer, breathing slow. Not all of Pangea is desert. Toward the cooler south, across the lowlands of the great landmass that geologists call Gondwana, the country changes. Here the floodplains run wetter, threaded with slow rivers and boggy hollows, and out of that damp ground rises a forest unlike any you have stood in. These are the Glossopteris forests, named for their most common tree, a seed fern with broad tongue-shaped leaves that fall in drifts when the cool season comes. They are not flowering trees. No flower has yet opened anywhere on Earth. They reproduce by seed and spore, and they grow in dense stands across the southern plains, their roots knitting through the wet peat. That peat matters more than it looks. Season after season, the fallen Glossopteris leaves and the dead wood pile into the swamps and slowly compress. Over immense stretches of time, that buried plant matter becomes coal. The vast coal seams that later ages would find across the southern continents were laid down here, in these quiet, cool forests, leaf by leaf, in the last chapters of the Permian. You're standing inside the making of them. The light in these forests is green and low. The canopy is not tall by the standard of later ages, but it is thick, and it filters the sun into a soft underwater dimness. The ground is spongy underfoot, dark with water, and the air holds the smell of wet decay and cold sap. It is a patient smell, the smell of a world composting itself. Listen, and you will notice what is missing. There is no birdsong. There will be no bird on Earth for something like 170 million years yet, no feathered thing to pipe from a branch at dawn. There is no chorus of the kind your own evenings know. What fills the air instead is older and stranger. It is the dry click and rasp of large insects, the stridulations of Paleozoic bugs working their wings and legs together into thin sawing notes. Insects have already been on this planet for a very long time, and they have grown into forms and sizes that later, richer oxygen ages permitted. They tick and buzz in the fern thickets, a percussion with no melody. Under that insect rhythm runs a lower sound. It is the grunting and low bellowing of the animals that rule this land, the tusked plant-eaters moving through the undergrowth, snapping stems, shouldering aside the ferns. These are the therapsids, the great branch of the tree of life that leads, across an unimaginable distance of time toward mammals, toward warm blood, toward you. In the Permian, they are not small and hidden. They are the dominant land vertebrates of the world, and they come in a bewildering variety of shapes. The most common of them, in the southern lands, is a beast that gives its name to a whole slice of geological time. It is called dicynodon, and it is a tusked, beaked, barrel-bodied herbivore, so abundant in the uppermost Permian rocks of southern Africa that paleontologists named an entire assemblage zone after it. When later scientists dug into the Karoo Basin of South Africa and read the layered stone like the pages of a ledger, they found dicynodon everywhere in the highest Permian beds, one of the most common large animals on the face of the earth for millions of years. Its name means two dog teeth, for the pair of tusks that jut from its upper jaw. Behind those tusks, the mouth ends in a horny beak, cropping vegetation the way a turtle's would. Picture one at the edge of a fern thicket in the last light of a Permian day. It is heavy through the chest and short in the leg, unhurried, grinding leaves with a sideways working of its beak. Its small eyes catch the low sun. It grunts, a flat wet sound, and another answers from deeper in the green. These animals have known this world for so long and so completely that their calm seems like a kind of birthright. They do not know that their kind is being written into the rock as a marker, a line that a future science will use to measure the end of an age. Move through the same country, and you meet a smaller cousin, and this one you might almost miss. It is Dictodon, a little dicynodont only about 18 inches long, roughly the length of your forearm and hand together. It is one of the most abundant vertebrates of its time, a modest plant-eater that has solved the problem of the brutal interior in the oldest way there is. It digs. Dictodon burrows down into the floodplain sediment and corkscrews as it goes, carving a spiral shaft that descends as much as 5 feet beneath the surface. When later paleontologists found these burrows fossilized, filled in and hardened into stone, they could trace the exact helical path the little animal had cut, turn by patient turn, and sometimes at the bottom of the spiral they found the digger itself, curled in its final chamber. Down there the killing swing of the surface temperature flattens out. 5 feet of earth is a good blanket. The oven heat of noon and the frost of the winter dawn both soften to something a small body can survive. Those spiral burrows did more than shelter one animal from the weather. In some of them, paleontologists have found more than a single occupant. They have found adults together with the small bones of the very young, which suggests these shafts were nurseries as well as refuges, places where a generation was raised in the cool dark below the cracking plain. It is a tender detail to carry with you, an image of parental care worked into the deep Permian earth, tens of millions of years before any creature you would call familiar walked the world. Not everything here is small or peaceable. Push north and east into the drier heart of the northern Pangean lands that would one day become Russia, and the cast of characters grows heavier and more armoured. Here lumbers Scutosaurus, a name that means shield lizard, though it is not a lizard in the sense you might mean. It is a pareiasaur, a broad, blunt, slow-moving plant-eater sheathed in bony armour. Scutosaurus runs 8 to 10 feet long, roughly the length of a small car, and it is built like a walking boulder. Knobs and plates of bone stud its thick hide. Bony bosses ridge its skull. It carries all of that on stumpy pillar legs, and by the best volumetric reconstructions its weight may have climbed toward 2,500 pounds, better than a ton of armoured herbivore grinding across the floodplain. Nothing about Scutosaurus is quick. It does not need to be. Its defence is mass and armour, the simple refusal to be easily killed. It plods from one stand of vegetation to the next, stripping the low plants, its wide gut fermenting the tough Permian greenery into fuel. When it lies down at the end of a hot day, it settles like a fallen wall, and the dust it stirs drifts and resettles fine as flour over the plates of its back. But armour exists because there is something to armour against, And in the Permian, the thing to fear has a face out of the oldest nightmares your lineage carries. The apex hunters of this world are the gorgonopsians, saber-toothed therapsids that stand at the very top of the food web. They are cousins, distant and terrible, of the same broad group that leads toward mammals, which means the great predators of this age are closer kin to you than to any reptile alive today. Gorgonopsians come in a range of sizes. Many run 3 to 10 feet in length, with body weights that in the larger forms could approach 600 pounds. They move on legs held more upright beneath the body than a sprawling reptile's, posture that hints at speed and stamina. But it is their teeth that seize the eye. A gorgonopsian's upper jaw carries a pair of long, curved canines, sabres of bone and enamel built for driving deep into flesh. The largest of them, in the late Permian of Russia, was a monster called Inostransevia. By different estimates, it stretched something like 10 to 14 feet from nose to tail, and its weight has been placed anywhere from around 1,100 pounds to well over 1,500, depending on how the reconstruction is done. Its upper canines have been reported at up to 6 inches long, longer than your hand, curved like drawn blades. Inostransevia was among the largest land predators of its entire world, and when it moved through the undergrowth toward a grazing Scutosaurus or a herd of dicynodonts, it was the most dangerous thing that existed. Hold the scene a moment. A gorgonopsian at rest in the shade is not the snarling engine of a museum mount. It lies low, flanks rising and falling, the great canines half hidden behind its lips, eyes tracking the movement of prey across the shimmering flat. When it rises to hunt, it does so with an economy that comes from being at the top for a very long time. There is no rival above it. No group of mammal-line predators would ever again reach quite this scale in quite this way, not for an enormous span of time to come. For now, in the last Permian afternoons, the saber-tooths own the world their prey has fattened. This, then, is the living Earth of 252 million years ago. Tusked herbivores in their millions cropping the fern thickets, armoured giants plodding the floodplains, saber-toothed hunters holding the high ground of the food web, small diggers spiralling down into the cool earth to raise their young, broad seed fern forests laying down the coal of ages in the cool wet south. It is a full world, a settled world, and by many measures it is life at its most established and complex since the Cambrian explosion set the whole animal experiment running hundreds of millions of years before. That is worth sitting with, because it is the true measure of what is coming. This is not a thin or struggling biosphere, this is the opposite. Across the long Permian, life had spread and specialized and knitted itself into deep, intricate food webs on land and in the sea. In the warm shallows around the edges of Panthalassa, reefs stood built by corals of kinds that no longer exist. The rugose and tabulate corals, reef builders that had laboured at their work since ages before the Permian even began. Brachiopods, shelled animals that look a little like clams but are built on an entirely separate plan, carpeted the seafloor in beds so dense they defined the ocean bottom. They had ruled that seafloor for something like 280 million years. On the open shelves crawled the trilobites, those segmented armoured animals that had been a signature of the seas since the Cambrian, survivors of more than 270 million years of prior history, patient and successful beyond easy comprehension. Everything about this world says permanence. The same broad kinds of animals appear in the rock, layer after layer, for stretches of time so long they defeat the imagination. If you had stood on a Permian shore and been told that nearly all of it, the corals and the brachiopods and the trilobites, the tusked herds and the saber-tooths and the armoured giants, would soon be gone, you would have had no reason to believe it. Nothing in the daily life of this earth points toward an ending. The insects click in the ferns, the dicynodonts grunt and feed, the heat comes and goes with the turning of the long seasons, and yet the rock, read carefully, tells a stranger and sadder tale than any single afternoon reveals. Life had already been tested once, not so long before, in the terms that deep time uses for not long. Roughly 9 or 10 million years earlier, a smaller crisis had passed through the Permian world, a pulse of extinction that some scientists now call the Capitanian event, tied to an earlier separate episode of volcanism far to the east. It thinned the ranks of many groups without ending the age. Whether it is best understood as a true separate catastrophe or as an early tremor of what was coming remains a matter of honest debate among researchers, but it is a reminder written into the stone that this settled world had already felt the ground shift once, and had recovered, and had gone on grazing and hunting as though the shifting could not happen again. Let yourself feel how quiet it is at the close of one of these Permian days. The sun sinks toward the flat far edge of the supercontinent, and the light turns the dust in the air to a hanging gold. The oven heat of noon eases by slow degrees. In the fern thickets, the great tusked herbivores settle in for the night, their bellows dropping to occasional grunts. The insects raise their dry soaring chorus a notch as the temperature falls. A gorgonopsian lifts its heavy head, tests the cooling air and lies back down. Somewhere beneath the plain a dicynodont turns in the bottom of its spiral burrow, 5 feet down in the dark, warm against the young curled beside it. Take one slow breath of that ancient air, cool now and smelling of wet fern and settling dust, and understand that you are breathing in the most complete living world the planet had built in 250 million years. There is a hard truth folded into the beauty of it, and it is the whole reason to tell the story of this place at all. Every one of these animals, the tusked and the armoured and the saber-toothed, belongs to the last full generation of a world about to end. The number that opens this account, 9 out of every 10 living things, is not a figure from some other lesser planet. It is a figure about this one, about these ferns and these grunting herds and these warm, shallow reefs. What is coming will not be a slow fading of one kind giving way politely to another. It will be the closest that life on Earth has ever come, before or since, to simply switching off. But not yet. Not on this evening. On this evening the world is whole, and it does not know. The animals lie down in a Pangea that has stood as one continent for so long, it seems it always will. The Glossopterus leaves drift down onto the dark peat, adding another thin page to coal seams no eye will ever read as coal. The one great ocean rocks against the one great shore under a sky just beginning to prick with stars, and the saber-toothed sleep with their long canines sheathed, dreaming, if they dream at all, of nothing but the next day's hunt. For 100 million years the mammal-line animals had been learning to run this world, and here at the Permian's end they were going to hand it, though none of them could know it, to something else entirely. That handing off is what all the rest of this account will follow, across the fire and the heat and the silence and the long, long recovery. For now, hold only this: a full earth, a warm evening, a world at rest and certain of itself. Before the ground stirs anywhere, walk slowly through the ranks of the animals that owned this world, not as legends, as bodies with weights, with dates, with teeth you could measure. Begin with the largest hunter Russia has yet given up from these rocks, Inostrans via, a gorgonopsian, which means a member of the mammal line, one of the distant proto-mammal cousins that ruled the land long before any true mammal existed. Picture something built low and heavy, roughly 10 to 14 feet from blunt snout to tapering tail. The size estimates vary by study, and honesty matters here, so hold them loosely. Different reconstructions put its weight anywhere from around 1,100 pounds to more than 1,700. Somewhere in that range walked a predator that had no equal on its stretch of Pangea. The teeth are what stay with you. Inostransevia carried a pair of upper canines reported up to about 6 inches long. Hold your hand in the dark and look at your index finger. That is the length of a single tooth, curved, edged, driven downward by jaw muscles anchored to a skull built like a wedge. These were saber teeth on a body the weight of a small horse. Nothing about the animal was fast in the way you might imagine a chase. It was patient, ambush-shaped, a slow closing of distance and then a single committed bite. Gorgonopsians as a family were the apex predators of the late Permian, and they came in many sizes. Most range from about 3 to 10 feet long, weighing up to roughly 660 pounds. Inostrancevia sat at the very top of that spread, an outlier in scale. And here is the quiet fact that gives this whole gallery its weight. Every Gorgonopsian, the small ones and the great ones alike, died at the Permian boundary. All of them. No animal of the mammal line would hold apex predator status at that size again for a very long stretch of time. When you look at Inostrancevia, you are looking at the last of a kind of ruler, near the end of its reign, though the animal itself could not have known it. Now change the shape entirely. Set the hunter aside and stand a plant eater in front of you instead. Scutosaurus karpinski. Not a mammal cousin at all, but a parareptile, from a wholly different branch of the family tree. Where Inostrancevia was built to close and kill, Scutosaurus was built to endure being attacked. The name points at its defense. Bony plates and lumps studded the thick hide, armor grown into the skin along the flanks and back and the sides of the skull. It stood about 8 to 10 feet long, and it was massive out of all proportion to that length. The mass estimate is the astonishing number. A volumetric reconstruction, the method where researchers model the whole body in 3 dimensions and calculate its likely volume, puts Scutosaurus at up to roughly 2,500 pounds, over a ton of armoured herbivore on stumpy pillar-like legs. It did not run from anything. It could not. Imagine a parked boulder that breathes grey and still in the heat, then slowly turns its blunt head toward you. That is closer to the truth than any lizard you have pictured. It moved at the pace of something that has no reason to hurry, cropping low vegetation, digesting it in a gut large enough to ferment the tough Permian plants that carpeted the floodplains. The dates matter too, and they place this animal right on the knife edge. The rocks that hold Scutosaurus sit at roughly 252 to 248 million years old in the source literature. That span straddles the extinction interval itself. This armoured giant lived in the final chapter, in the years when the sky was beginning to haze over with sulfur and ash, drifting from eruptions thousands of miles to the north. Its armour could turn the teeth of a gorgonopsian. It could do nothing at all about a warming world and a failing food supply. Weight and plating are answers to one kind of threat. The threat that was coming had no shape a body could brace against. Now shrink the scale again, all the way down, because the Permian was not only giants. Kneel to the ground and meet Dictodon phylliceps, a small dicynodont, a member of the tusked, beaked, plant-eating group that was among the most abundant land animals of the entire period. Dictodon measured only about 18 inches long. You could cradle one in your arms. Where the gorgonopsian ruled by force and Scutosaurus by armour, Dictodon ruled by numbers and by a single brilliant trick. It dug. Down into the floodplain soil went spiral burrows, corkscrew shafts descending as deep as about 5 feet, before opening into a chamber at the bottom. Follow that shape in your mind. A tunnel that turns as it drops, so that the killing heat of the Pangean surface never reaches the bottom, so that a predator cannot simply reach in. Down there, in the cool and the dark, Dictodon sheltered from the brutal seasonal swings of the continental interior, the baking dust-dry summers and the frost-touched winters. And down there, researchers believe, it reared its young. Fossil burrows have preserved clustered neonates, tiny animals gathered together at the base of the spiral, which suggests the burrow was not only a refuge but a nursery. Think about what that means for the sound of this world. Beneath a plain that looked nearly empty at midday, the ground was quietly full. Thousands of small tusked animals resting in their spiral chambers, waiting out the heat, a hidden population threaded through the soil. Abundance was Dictodon's strategy. For millions of years across the middle and late Permian, it worked beautifully. And then it stopped working, and the disappearance of even this small, adaptable, well-sheltered digger becomes part of the record of the land die-off written into the Karoo rock of what is now South Africa. Which brings you to the last animal in this gallery, and the one whose name does the most quiet work in the whole science. Dicynodon, another tusked-beaked herbivore of the dicynodont group, so common in the uppermost Permian layers of the Karoo Basin that geologists named an entire slice of time after it. The rocks that record the very end of the Permian in that basin are known, in the classic scheme, as the Dicynodon Assemblage Zone, a biostratigraphic unit, which simply means a layer of rock defined by the fossils it contains rather than by its precise age in years. Where you find that assemblage, you are standing in the final act of the Permian world. Sit with why that is powerful. Dicynodon was everywhere. For a long time, one of the most common large animals on its part of the planet. It was the kind of creature you would have seen daily, moving in loose groups through the fern thickets, cropping vegetation with a horned beak, two short tusks jutting from the upper jaw. So ordinary that its presence became the background of an age. And then, in a rock layer barely a few feet thick, it is gone. That transition, the level where Dicynodon vanishes from the fossil record, is one of the clearest markers paleontologists have for the terrestrial extinction. When the most common animal in a landscape disappears, the disappearance leaves a signal you can read in stone millions of years later. The picture from the Karoo is not a single instant, and careful researchers are honest about that. The vertebrate record there suggests a gradual decline through the latest Permian, a thinning of the ranks, punctuated by a sharper extinction pulse right at the boundary that struck the Dicynodonts especially hard. More recent work argues this land crisis was essentially synchronous with the die-off in the seas, happening in step rather than lagging behind. But the tempo is still being refined, and the details are still debated. What is not in doubt is the outcome. The tusked herbivores that had defined the land for so long were cut down to almost nothing. So hold the four of them together in the dark, this gallery of the late Permian rulers. Inostrancivia, the saber-toothed hunter 10 to 14 feet of ambush and bone, canines the length of your finger. Scutosaurus the armoured ton, a breathing boulder that feared no tooth. Dictodon the digger, 18 inches of patience and spiral tunnels, hidden by the 1,000 beneath the plain. Dicynodon the commonplace so abundant that time itself was named for it. Predator and armoured prey, the small survivor and the ordinary multitude. Together they were the working machinery of a stable, ancient ecosystem, each with a role, each with a shape honed over millions of years to fit this warm, harsh, single-continent world. Remember the numbers, because the numbers are the point. Not one of these animals was fragile. They were large or armoured or clever or overwhelmingly numerous, which are the four classic ways a lineage buys itself security in a dangerous world. Inostrancivia had force. Scutosaurus had defence. Dictodon had shelter and hidden young. Dicynodon had sheer abundance. 4 different answers to the ordinary problems of survival, and all 4 written into the fossil record as success, right up until the moment none of them was enough. That is the strange lesson buried in this quiet gallery of bodies. The catastrophe that was gathering did not sort its victims by strength or size or cunning. It reached the giant and the digger alike. And while these animals went about their ordinary days across the southern lands, cropping ferns, minding burrows, closing on prey in the shimmering heat, the source of their undoing was already at work, far away and out of sight, deep beneath a landscape none of them would ever see. Far to the north, beneath a quiet plain, the ground was already beginning to stir. Far to the north, beneath a quiet plain, the ground was already beginning to stir. Far to the north, beneath a quiet plain, the ground was already beginning to stir. There were no eyes to watch it happen, and no ears close enough to catch the first low complaints of the rock. In what you would one day call Siberia, the crust had grown thin and restless above a slow-rising column of heat. For a long while the surface gave nothing away. The seed fern forests stood. The rivers ran their brown, unhurried courses toward a shallow sea. Underneath, though, pressure was gathering, patient and enormous, the way weight leans against a door that has not yet swung open. Settle in for this part. You do not need to hold any single number in your hands. Let the figures drift past you like weather, and let the calm of a world about to change move slowly under your breath. What began there is called, today, a large igneous province. It is a plain phrase for one of the most violent things the planet knows how to do. Not a single volcano, not a single mountain with a smoking cone, but a vast region of the crust opening in long cracks and bleeding lava across the land for an almost unimaginable stretch of time. The name given to this one is the Siberian Traps. The word traps comes from an old term for stairs, because the cooled lava stacks in step after step of dark rock, ledge above ledge, like a staircase built for something far larger than you. The main pulse of that eruption fell roughly between 252.3 and 251.4 million years ago. Hold those two dates gently, one against the other. The gap between them is well under 1,000,000 years, which sounds like forever, and is to the Earth a short and terrible breath. That window overlaps almost exactly with the greatest dying life has ever suffered. When you line up the timing of the lava and the timing of the loss, they sit one on top of the other, and that overlap is the reason so many careful minds have spent their whole lives on this cold northern rock. Try to feel the size of what came out of the ground. Estimates of the erupted material run to something like 3 to 4 million cubic kilometers of lava and volcanic rock. In the units you may find easier to picture, that is on the order of 750,000 to nearly 1,000,000 cubic miles of molten stone. Numbers that large stop meaning anything on their own, so let us set them against something you know. Imagine the entire lower stretch of the United States, coast to coast, border to border, every plain and city and mountain range. Now imagine all of it buried under lava to a depth of 1/2 a mile. That is the scale the geologists reach for when they try to make you feel it. Enough rock to drown a continent past its rooftops, past its hills, past almost everything but its tallest peaks. Even the leftover worn-down remains are staggering. The basalt you can still walk on in Siberia today, after 250 million years of erosion stripping it away, covers roughly 2 million square kilometers. That is close to 770,000 square miles of exposed dark stone, an area larger than Alaska and Texas combined. And that is only what survives at the surface. Researchers who study the buried edges of the flows argue the original province reached farther still, its lower layers hidden now beneath younger sediment, its true footprint larger than the map can easily show. What you see is the wreckage. The living eruption was greater. Stand in your mind at the edge of one of those early flows. Picture a wall of black rock stacked taller than you, ledge on ledge, running away in both directions until it simply meets the horizon and keeps going. Not a cliff you could walk around in a day. A front of cooling basalt stretching for hundreds of miles, breathing heat into a sky already thick with ash. The air smells of sulfur and hot iron. The ground ticks and cracks as fresh lava cools. And this is not a single afternoon of fury. This is the rhythm of the land for thousands of years at a stretch. Eruption after eruption, flow over flow, each new sheet of molten rock spreading across the cooled and blackened skin of the last. For a long time, that image of surface lava was the whole picture in most minds. Rivers of glowing rock, a poisoned sky, a landscape charred and buried, and that alone would have been a catastrophe worth remembering. But the more closely researchers looked, the more they came to suspect that the open flood lavas, terrible as they were, may not have been the true engine of the dying. The deadliest work the leading idea now holds happened out of sight, underground, where the magma never reached the air at all. Here is the crucial shift, and it is worth slowing down for. As the eruption matured, its style appears to have changed. Instead of only pouring lava out across the surface, more and more of the rising magma stalled below ground and spread sideways between existing layers of rock. Those flat, intruding sheets of magma are called sills. Picture hot rock forcing its way horizontally into the buried pages of the crust, prying them apart, settling in as glowing sheets that might run for tens of miles. And the ground it pushed into was not ordinary ground. It was a thick basin of sedimentary rock, layer upon layer laid down over hundreds of millions of years, and it was loaded with exactly the wrong things. That buried basin held coal from ancient swamps pressed slowly into carbon-rich stone. It held evaporates, the salt and mineral crusts left behind by seas that had dried away. It held organic shale, dark mud rock thick with the remains of old life. In quiet times, those rocks are simply archives, cold and still. But the sills arrived like a lid closing over a fire. The heat of that intruding magma soaked outward into the surrounding rock, and the coal and salt and shale began to bake. Think of how warmth spreads through a closed room from a stove you cannot see. That is the closest small thing your body knows to what happened across whole regions of buried Siberia. Sill heat rising through bedrock like warmth through a closed lid, patient and total, cooking the rock from within. And baked rock does not stay silent. Heat that intense breaks the buried carbon and salt and organic matter apart, and what it releases is gas. Not a little, not locally. Vast pulses of it, carbon dioxide and methane and a cocktail of sulfur and halogen compounds, driven out of the cooking sediment and forced up through the fractured crust toward the sky. That is the idea that reframed the whole event. The lava you can picture, the black flows and the burning horizon, poured out its own carbon and sulfur, and that mattered. But the sills reaching into coal and salt and shale may have released far more, a second and larger budget of greenhouse and poison gas that the lava alone could never account for. The rock the magma touched was fuel. And there was, buried beneath that quiet Siberian plain, a staggering amount of fuel waiting. Let me pause the story for just a moment, because this is roughly the middle of our long night together, and I would like to say one plain thing before we go on. If these slow walks through deep time keep you company, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then let it go, and sink back down into the warmth of the buried rock. There is a great deal of quiet left ahead of us. Now, the gas. When you cook coal and organic shale at depth, the most obvious thing you make is carbon dioxide, the same gas that thickens an atmosphere and traps the sun's warmth against the ground. Pour enough of it into the air over enough centuries, and the whole planet begins to hold heat it once let go. But carbon dioxide was only part of the load. The eruption and the baking sediment together released enormous quantities of sulfur, which hazes the sky and sours the rain. They released halogen compounds, a kind of chemistry that can gnaw at the high shield of ozone that softens the sun's harder light. Each of these on its own is a stress a healthy world might shrug off. Arriving together, pulse after pulse, across thousands of years, they became something else. And there is one more signature in the rock, small and strange and specific, that ties this northern eruption to the dying all around the globe: nickel. The Siberian magma was unusually rich in it, and as it erupted and degassed, it appears to have thrown fine nickel-bearing particles high into the atmosphere. Those particles drifted on the winds, settled through the air, and rained down into sediments far from Siberia, into layers of mud that would one day be lifted into hills on the far side of the world. When researchers measure the chemistry of nickel in rocks from the boundary, they find a fingerprint that points back to those aerosols. Recorded globally, a thin metallic whisper laid across the planet at exactly the wrong moment. Why should a scatter of nickel matter to living things? The idea, and it is still being tested, is that this sudden gift of metal could have fed certain microbes in the sea, tipping ocean chemistry towards states that living animals could not survive. Some researchers go further and suggest the nickel may have disturbed the balance of microbes that consume methane, letting more of that powerful warming gas linger in the air. A dusting of metal, invisible to any eye, quietly nudging the chemistry of a whole ocean and a whole atmosphere. It is a reminder that in a catastrophe this large, the smallest ingredients can carry outsized weight. So gather the pieces of the trigger in your mind, slowly, the way you might lay out stones on a windowsill. A region of crust splitting open across an area larger than most nations. Lava enough to bury a continent half a mile deep. A shift, over time, from open flows to hidden sills. Those sills baking coal and salt and organic shale, until the buried rock exhaled carbon and sulfur and halogens in pulses far beyond what the lava alone could give. And through it all, fine nickel aerosols drifting down over the entire planet. This is the leading candidate for what set the Great Dying in motion. When people ask what pulled the trigger on the end of the Permian, this cold northern province is the name they reach for first. But I want to be honest with you, in the calm way this quiet hour asks for, because the truth is more interesting than a tidy answer. The Siberian Traps are the leading suspect. They are not a closed case. To say the eruption is the trigger is not the same as saying it was the sole and proven cause of every death that followed. What researchers can show with real confidence is the timing, the volume, the chemistry, and the global fingerprints. What remains genuinely debated is the precise chain of consequences, how much weight to give the heat, how much to the acid, how much to the loss of oxygen in the water, how much to the poisons that came after. Most who study it now picture not one clean killer but a cascade, a series of blows landing one after another, each making the next more deadly. There is even a live argument about whether the late Permian suffered one great catastrophe or two. Some researchers point to a smaller, earlier crisis, roughly 9 to 10 million years before the main event, tied to a separate and older pulse of volcanism far away. If they are right, the world was already wounded, already thinned and stressed when the Siberian Traps opened. A planet struck once and still healing, struck again far harder. That earlier blow is not settled either, but it sits in the background of this story like a bruise beneath new skin, a warning that the world had been tested before the worst arrived. Hold, too, the honest uncertainty about tempo. Some records suggest the core of the extinction was astonishingly fast, unfolding across tens of thousands of years, quick enough that against the long calendar of the rock it reads almost as a single event, a geological instant of loss. Other records, especially from the plants and the land animals, suggest a more drawn-out decline, a fading that began before the sharp boundary and dragged on after it. Both signals are real. The likeliest truth is that the catastrophe had a fast, brutal heart, wrapped in a slower, sadder decline on either side. Higher precision dating keeps refining the picture, year by year, and the honest answer is that the exact rhythm of the dying is still being measured. None of this doubt weakens the central image. If anything, it deepens it. Somewhere beneath a quiet Siberian plain, a column of heat opened the crust, and for the better part of 1 million years the ground bled lava and breathed poison into the sky. The rock the magma cooked held the fuel that would, in time, undo the living world, and this is the moment that would come to change everything that walked and swam and crawled across Pangea. Not because the lava reached them. Almost none of the dying happened anywhere near the flows. The animals of southern Africa, the reefs of the shallow tropical seas, the forests of the far south, none of them would ever feel the heat of a single Siberian eruption directly. That is the strange, quiet horror of what began here. Picture it once more before we move on. The land far to the north, black and steaming, ledge of cooled basalt stacked on ledge, that wall of dark rock running to the horizon and beyond, and all around the rest of the world for now, an ordinary day. Tusked plant-eaters grazing the fern thickets, armoured heavy-bodied browsers moving through the lowlands, some of them well over 1,000 pounds, plodding between stands of broad-leaved seed ferns. Saber-toothed hunters, the largest of them stretching perhaps 10 to 14 feet from nose to tail. exposing through the heat of the afternoon. Small burrowing herbivores curled in their spiral tunnels, 5 feet down in the cool earth, waiting out the dry. None of them aware that anything at all has changed. The sky in their world is still their own sky. The link between that northern rock and those distant, unsuspecting animals was never going to be the lava. It was always something thinner, something that could travel, something that could reach a fern thicket 10,000 miles away without a single drop of molten stone crossing the distance. The connection was the air. The carbon and the sulfur, the halogens and the fine metallic dust, all of it rising from the cooking rock and spreading on the winds until there was no corner of the planet the eruption could not touch by breath alone. So let the picture settle as you drift. A wounded patch of ground in the north, exhaling for 10,000 centuries. A world elsewhere still green and warm and full, going about its slow days in the last long light before the change. And between the two, invisible, patient, already thickening, the atmosphere itself beginning to carry the message outward. You might wonder how anyone speaks with such confidence about a single year, buried so unthinkably far behind you. The certainty does not come from guessing. It comes from reading rock the way you would read the growth rings of an old tree, one thin band at a time, each band a season the world can no longer forget. Begin where the timekeepers begin, at a quarry called Meishan in Zhejiang province in eastern China. Here a hillside of pale limestone has been split and numbered, bed by bed, into a patient stack of counted layers. Geologists call this place a global stratotype section and point. It is the agreed reference, the master ruler against which every rock of this age anywhere on Earth is measured. The boundary between the Permian and the Triassic is not fixed by opinion or by preference. It is fixed here at the base of a thin layer labelled Bed 27C. That layer is a modest thing. You could cover it with an open hand and have fingers to spare. Yet its base marks the formal floor of a new chapter of Earth history, dated to roughly 251.9 million years ago. Just below it, in the darker clays, the old world is still crowded with shelled life. Just above, much of that life is simply absent. The line you would trace with a single fingertip separates a full ocean from an emptied one. The number itself, 251.9 million years, is the harder trick to earn. To pin a precise date onto a layer of ancient mud, you need a natural clock sealed inside it. That clock is a mineral called zircon. Zircons are tiny. Most are no larger than a grain of sand, and many are smaller than a mote of dust drifting through a shaft of light. They form in cooling magma and in the ash that volcanoes fling high into the sky. When that ash settles onto a seafloor and hardens into stone, it locks a scattering of these crystals into the layer forever. Each one is a sealed vault, and each one, at the moment it first crystallized, struck a quiet bargain with time. Here is the bargain. A forming zircon readily accepts atoms of uranium into its structure. It refuses lead almost entirely. So a fresh crystal begins its life carrying uranium and effectively no lead at all. That single detail is everything. Because uranium is unstable. It decays, atom by atom, into lead, at a pace that never changes and never hurries, indifferent to heat, to pressure, to the wide silence of the years passing over it. Uranium-238 turns into lead-206, with a half-life of about 4.5 billion years, slow beyond ordinary imagining. A second form, uranium-235, decays into lead-207 far more quickly. So every zircon carries two clocks running side by side at two different speeds. When you measure how much lead now sits beside the surviving uranium, you are counting how many atoms have quietly made that crossing. Two clocks that agree with each other give you a date you can lean your weight on. It is as close as deep time comes to a stamped receipt. The crystal itself holding the paper, the ink already dried before the first dinosaur drew breath. The measuring is slow, careful work. A single crystal is dissolved, its uranium and its lead teased apart atom from atom, then weighed on instruments that can sense a difference of a few atoms among many billions. Done well, on the cleanest crystals, this method can fix an age hundreds of millions of years old to within a few tens of thousands of years. On the scale of what you are picturing tonight, that is a startlingly sharp edge to hold. Now carry that sharp edge north, to Siberia. The great eruptions left their own ash and their own crystals behind. Dateable zircons sit inside the volcanic rock itself and in the layers baked and buried around it. When those crystals are read the same patient way, they bracket the main violent pulse of the Siberian Traps to a window between roughly 252.3 and 251.4 million years ago. That is well under a single million years for the very worst of it. Against the 4.5 billion year age of the Earth, it is a knife stroke, over almost before it began. Lay the two timelines gently over each other, and the case begins to build itself. The Siberian eruptions climb toward their peak. The crystals at Meshen fix the Great Dying at about 251.9 million years, sitting squarely inside that eruptive window. The burning and the killing share the same narrow slot of time, at the same depth in the rock. Cause and casualty, stacked one atop the other, waiting to be read. But overlap in time is not the same thing as proof, and the careful ones say so out loud. Two events can share a moment without one driving the other, so the dating alone does not close the argument. It sets the stage, rules out rival timings, and narrows the field of suspects. Where the numbers still carry doubt, the honest researchers leave that doubt in plain view rather than paint smoothly over it. The exact tempo of the dying is still being sharpened. Some rocks suggest the core of it was brutally fast, a matter of tens of thousands of years. Others hint at a longer decline, drawn out across the boundary. This is where a second kind of reading helps. The chemistry of the seawater itself is recorded in stacked bands. Oxygen isotopes and carbon isotopes layered through the limestone like the rings of a tree, each thin ring holding the temperature and the breath of one slice of that vanished ocean. Read together. The clocks and the chemical rings tighten the picture that any one thread alone would leave loose, and so the timekeepers reach for one more independent line of evidence. Not a clock this time, but a fingerprint. That fingerprint is nickel. The Siberian magmas were unusually rich in it, and the eruptions lofted fine nickel-bearing particles high into the atmosphere, where the winds took hold and carried them across the whole face of the planet. Those particles drifted down into seafloors and lake beds thousands of miles from Siberia, and settled quietly into the mud alongside everything else that was falling in those years. Nickel comes in slightly different weights, called isotopes, and volcanic nickel carries a particular blend of them, a chemical signature as specific as a maker's mark. When researchers draw nickel out of sediments laid down right at the boundary, in places far removed from the eruptions themselves, they keep finding that same telltale volcanic blend. The air over those distant, quiet coasts had been dusted with Siberia. The eruption had exhaled, and the whole world breathed it in. That nickel may have done more than simply drift and settle. Researchers have proposed that it fertilized changes in ocean chemistry, and that it may have starved certain microbes, the ones that normally consume methane, tilting the seas further toward crisis. The details are still being worked out, carefully and slowly, and stated as possibility rather than certainty. But the fingerprint itself is hard to argue with. It ties the far corners of the globe directly back to a single erupting scar in the north. So consider what the rock now hands you, quietly, without any need to raise its voice. A boundary fixed at the base of a hand-sized layer at Meshen. A date near 251.9 million years, drawn from crystals that behave like sealed receipts of time. A Siberian pulse braced tightly into the same slender window, and a nickel fingerprint dusted into distant mud, proof that the eruption's reach extended far beyond the reach of its lava. The eruptions never stayed in Siberia. Their breath crossed every ocean and touched every shore. The lava was only the opening move, and the air itself would carry the rest. The lava was only the opening move, and the air itself would carry the rest. The lava was only the opening move, and the air itself would carry the rest. Picture the sky above the late Permian world, thousands of miles from Siberia, and still it is changing. You cannot see carbon dioxide. You cannot smell it. But it gathers in the high air like a slow tide coming in, and it holds the sun's heat close against the skin of the planet. The eruptions bake volatile rock underground, coal and salt and oily shale, and every buried thing they touch is exhaled into the atmosphere. The lava built the furnace. The gases are what carry the heat outward, across every ocean into every breath. Come down close to the equator now, to a shallow sea that once teemed with life. For a moment, imagine this water the way it was before, warm as a summer bath and no warmer, close to 70 degrees Fahrenheit at the surface. It was rich then, it was crowded. Now stand in that same shoreline shallows and feel the change move through it. The heat climbs, not in a day, not in a year, but across many thousands of years, degree by patient degree, the surface warms toward the high 90s. By some reconstructions, the water pushes past 104 degrees Fahrenheit, hot enough that the sea, near the equator, becomes a place life must flee rather than a place it can hold. These are estimates, and you should hold them gently. They come from oxygen locked inside the tiny hard mouth parts of eel-like animals called conodonts, chemical thermometers buried in stone. Reading them is careful work and the numbers carry a margin. But the direction is not in doubt. The equatorial ocean warmed, and it warmed severely, and somewhere near the boundary the tropics became a heat that living tissue could not carry. Some researchers argue the warmest belt of the sea became a temporary dead zone, driving what survived toward cooler water far to the north and far to the south. Try to feel it from inside a body. The heat haze hangs over the coast thick as standing in warm bath water, the horizon smeared and trembling. There is no cool current to swim toward, no deep shade of cold water below. Warm water holds less oxygen than cool water. So as the sea heats, the very gas that animals need thins out of it. Exactly when their bodies, running hotter, need more, the warmth speeds their inner chemistry. Their demand climbs, the supply falls. That squeeze between rising need and falling breath is one of the quiet killers here, and it works without a single wave of violence. A study published in 2026 measured this squeeze in living animals rather than in stone. Researchers put modern brachiopods and clams into tanks and slowly warmed the water, watching how much oxygen each body burned. The old armoured shellfish, the brachiopods, could not keep pace. Their oxygen demand rose faster than they could feed it. The more flexible bivalves, the clams and their kin, adjusted and endured. Brachiopods had ruled the seafloor for some 280 million years. Warming of roughly 8 to 12 degrees Celsius, unfolding over thousands of years, was enough to overturn a reign that long. The experiment was run in a laboratory, not on the ancient boundary itself, so it is a window onto the mechanism rather than a photograph of the event. But it puts a measured number under an old suspicion. Heat alone, patiently applied, can undo a body plan that time itself had blessed. Heat is only the first edge of the cascade. The same carbon dioxide that warms the sky does something else when it meets the sea. It dissolves. It reacts with seawater and turns part of it to acid, and the ocean's chemistry begins to lurch sideways. You can read that lurch in the rock at Meishan, in Zhejiang province in China, where a thin, dark clay layer marks the boundary in a quarry wall. The carbon signal there swings hard and fast, a sharp jolt recorded in the isotopes, the chemical bookkeeping of a planet exhaling too much carbon too quickly for the sea to absorb in peace. To understand what acidification does, hold a seashell in your mind. It is built of calcium carbonate, laid down atom by the animal that grows it, drawn from the water around it. Corals do this. Clams do this. brachiopods, sea lilies, the lacy colonies of bryozoans, the reef-building sponges. Two crystal forms carry most of this work, calcite and aragonite, and both depend on the water staying friendly to their chemistry. When the sea grows more acidic, that friendliness fails. It becomes harder to pull carbonate from the water and lock it into a shell. In the worst of it, the water can begin to eat its shells already made, dissolving the armour faster than the animal can repair it. So imagine an animal that must build its own house from a material the water is quietly turning to poison. Every hour it spends making shell is an hour spent against a rising current. The young suffer first, the larvae with their thin new skeletons, too fragile to win that race. This is why the extinction fell so hard on the heavily armoured and the slow. Among marine invertebrates, roughly 81% of the genera that carried thick calcareous skeletons and breathed inefficiently were lost. Calcareous sponges, rugose corals and tabulate corals, the great reef builders of the older seas, brachiopods, bryozoans, the stalked sea lilies. The animals least able to adjust their inner chemistry were the animals the changing water struck hardest. The rugose and tabulate corals had built reefs since the Ordovician and the Silurian, hundreds of millions of years of steady architecture rising from the seafloor. At the end of the Permian they went fully extinct, both groups entirely, and with them the reefs themselves vanished from the world's record for millions of years. Picture a shallow tropical sea stripped of its coral cities, the drowned scaffolding gone quiet and then gone entirely, the fish and the swimming things that sheltered there scattered into open water with nowhere left to hide. It would be a very long time before new corals, the scleractinians, rose in the warm Triassic seas to build again. I want to slow here and be honest with you about what we know and what we still argue over, because the truth of this event is more interesting than any single clean story. No one has proven that acidification alone did the killing. No one has proven that heat alone did it, or that the loss of oxygen did it by itself. Most researchers who study this boundary now treat these forces as a compounding cascade, a set of pressures arriving together and feeding one another, rather than one settled killer standing over the bodies. The heat drives out the oxygen. The carbon dioxide warms the sky and sours the sea at once. Each pressure weakens what the next pressure finishes. The relative weight of each, which mattered most, and where and when, is still actively studied, still being refined with sharper dating and better chemistry. That uncertainty is not a weakness in the account. It is the honest shape of a catastrophe with many hands. There is a third hand in this, and it may be the strangest. As the water warmed and soured, the sea began to lose its oxygen not only at the surface, but in vast volumes below. Geologists track this with elements that change their chemistry, depending on how much oxygen surrounds them, uranium above all, and other redox-sensitive metals that keep a faithful record in the mud. Read across many sites. Those proxies tell the same story. Immediately before and during the extinction interval, oceanic anoxia expanded rapidly and widely. Oxygen-starved water, which had lurked in the deep and in scattered basins, spread and rose and spilled across the shallow shelves where most sea life lived. Stand on that seafloor in your imagination, on a shallow shelf that only a little while ago was bright with shells and motion. The oxygen is gone from the water just above the mud. Nothing that needs to breathe can stay, and into that lifeless calm come organisms that thrive exactly where oxygen fails, the sulfate-reducing bacteria. They breathe sulfate instead of oxygen, and the waste of their breathing is hydrogen sulfide, the gas of rotten eggs. In healthy seas, these bacteria are pinned to the deep mud, walled off from the living world by a ceiling of oxygenated water. In a widely anoxic ocean, that ceiling thins and lifts. The hydrogen sulfide has room to climb. The seafloor answers this in colour. Where mineralised shellfish once crowded the bottom, the mud turns a sickly grey, and then a deeper grey-black, draped in microbial mats, slick sheets of bacteria spreading over ground that animals have abandoned. It is a strange still surface, smooth where it should be textured with burrows and shells, dark where it should be pale with broken carbonate. These mats are the flag of a sick ocean. They appear again and again in boundary rocks around the world, the same grey-black signature written into stone on far separated coasts. Follow the hydrogen sulfide upward now, out of the mud, up through the dead water toward the light. In the worst-hit shallow basins, some researchers propose, it did not stop at the surface. It welled up into the shallowest water and even breached into the air above. The gas is poison to almost everything that breathes with oxygen, to fish and to the marine reptiles hunting them, and along a poisoned coast it would leave a faint rotten egg tang drifting on the wind, thin at first, then unmistakable. Imagine walking a shoreline where the sea itself exhales that smell, where the tide brings not salt and life, but the sourness of a stagnant, breathless ocean. I should be careful here too. The idea that upwelling hydrogen sulfide killed on a large scale, in the water and possibly in the air, is a hypothesis, a proposed kill mechanism supported by chemistry and by modelling rather than proven beyond argument. The expansion of anoxia is well recorded in the isotopes. The presence of these bacteria and their gas in oxygen-starved water is understood. How far the poison actually reached, how much of the dying it directly caused, remains part of the open debate. What is not in doubt is the shape of the world it points to, a sea running out of breath, a seafloor gone grey and slick and silent, a sourness on the air where there had been the clean smell of a living ocean. If you have found any calm in walking through this slow undoing, and if you would like this quiet voice to keep carrying you through deep time on other nights, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. No need to rise, no need to reach for anything. Only let the old sea keep turning beneath you. Lift your gaze now from the water to the sky, over the whole doomed world, because the poison in the air was not only the invisible carbon and the faint sulfide smell of the coast. Sulfur poured from the eruptions in enormous quantity, and high in the atmosphere it formed a haze of fine aerosol particles, a pale veil drawn across the sun. Volcanic ash drifted with it, carried on the winds from Siberia across thousands of miles. So the light itself changed. The sky over Pangea hazed and dimmed, the sun going wan and smeared behind a curtain of sulphur and dust, the colour of the daylight turning strange and thin. There was something even more particular in that haze, a metal fingerprint. Nickel-rich aerosol particles chemically tied to the Siberian eruptions are found in boundary sediments all over the globe. Their presence is one of the clearest links between the volcanism in the far north and the crisis everywhere else. The nickel is more than a marker, though. Researchers have proposed that these particles altered ocean chemistry as they settled, fertilizing certain microbes and possibly suppressing the microbes that consume methane. Knock back the methane eaters, and more of that powerful warming gas escapes into the air, and the furnace burns a little hotter still. This too is a hypothesis under study, a strand in the tangled web rather than a proven lever. But the nickel itself is real, dusted into the rock across continents, a metal breath from a single wound in Siberia settling over the entire planet. Feel the air now the way a living animal would feel it in those long centuries. It is heavy. It is still. The greenhouse heat presses down day and night without the relief of a cool evening, and the humid, hazy calm sits on the land like a damp blanket laid over everything, hard to throw off, hard to breathe against. Along the tropical coast, the heat haze shimmers thick as warm bath water, the far shore dissolving in the wobble of hot air. There is a sourness on some of that wind. The light is dimmed and yellowed by sulphur, and it does not pass. Season after season, the weight stays. A world learning, slowly, to be a hothouse. For the shelled animals of the shallow sea, this is 3 sentences of doom read at once. The water is too hot, so their bodies burn oxygen faster. The water holds less oxygen because it is hot, and less still because anoxia is climbing the shelves. And the water is souring, so the shells they need to survive grow harder to build and easier to lose. Any one of these might be survived by a hardy animal in a good year. Arriving together over centuries with no cool water to flee to and no relief coming, they close every door at once. This is what a cascade means. Not one blow, but many, each landing where the last one left a bruise. You can see the selectivity of it in who suffered and who slipped through. The animals that could adjust their inner chemistry, that could breathe efficiently and tolerate low oxygen and warm water, had a chance. The clams, certain snails, the more flexible, more active bodies, the ones that could not, the armoured and the slow and the passively breathing, the brachiopods and corals and sea lilies that had ridden the stable seas for hundreds of millions of years, were caught in the exact grip that their old success had never prepared them for. Stability had been their whole world. When it broke, their patience became their doom. And the trilobites, those ancient segmented wanderers of the seafloor, were among the ones caught. They had survived since the Cambrian, some 270 million years of history behind them, through earlier extinctions, through changing seas and shifting continents, one of the great long-running lineages of animal life. At the end of the Permian they went fully extinct, every last one, their long deep run ending in this same warming, souring, breathless water. When a group that old and that tested simply stops, you begin to understand what pitch the crisis had reached. This was not a hard season. This was the removal of the ground beneath life itself. Hold all of it together in one slow image, the whole poisoned system at once. The sky hazed pale with sulfur and dusted with ash and nickel from a wound thousands of miles north. The air heavy and still and warm, pressing down like a damp blanket that will not lift. The equatorial surface water climbing past anything the old shelled life could bear. Toward the upper 90s and beyond, the coastal shallows shimmering with a heat haze thick as warm bath water. The carbon chemistry lurching sideways in the rock at Mation, the shells growing thin and failing to form in souring water, the oxygen bleeding out of the warming sea, the seafloor turning grey-black and slick under mats of bacteria that breathe where nothing else can, and a faint rotten egg tang lifting off the dead shallows into the strange dim light. Take one slow, deep breath of that imagined air, and you would taste the whole cascade in it at once, heat and sourness and sulphur braided together. There is a quiet mercy in how gradual it was, at least to the eye. No single terrible morning, no wall of fire sweeping the coast. If you could stand on a Permian shore across those long centuries, most days would look almost ordinary, the haze a little thicker, the water a little warmer, the shells a little scarcer in the tide pools than the year before. The catastrophe moved at the pace of chemistry, patient and nearly invisible, which is perhaps why it reached so far. Nothing could outrun a threat that arrived so slowly and yet left no cool corner of the world unchanged. The animals did not know they were inside the largest dying their planet had ever staged. They only knew the water was harder to breathe, and the shells harder to build, and the good places fewer with each turn of the seasons. We are still learning to weigh these forces against one another, and that ongoing work is going to keep refining the picture for years to come. Adjusting how much of the loss we assign to heat, how much to acid, how much to the breathless water and its rising poison. New tanks of living animals, new isotopes read from new sections of rock, new dates measured to finer precision. The honest answer, for now, is that they acted together, and that untangling them fully is the work of many careful hands across many years. What no one disputes is the outcome the cascade was building toward, out in the shallow seas where most of life still lived. So return there one last time, to the warm equatorial shallows under the hazed and yellowed sky. The corals are failing. The brachiopods cannot keep pace with their own need for breath. The sea lilies bow in water gone thin and sour. Below them the mud is turning grey-black, and a faint rotten egg breath is beginning to lift toward a dimmed and distant sun. Every measure of the water, its heat, its acid, its vanishing oxygen, has crossed from the world these animals were built for into a world they cannot hold. The furnace in the north still burns, and its breath has reached the farthest coast. Picture the ocean now as a room with a single lock and a ring of keys laid out beside it. Each key is a way the world might have killed nearly everything in the water. Researchers have spent decades trying them one after another, listening for the click that turns the whole mechanism. None of them turns it alone. That is the strange truth at the centre of this dying. There is no single murder weapon, only a crowd of them, working the same lock at once. Let the first key be heat, paired with its quieter partner, carbon dioxide poisoning. As the Siberian eruptions loaded the air with carbon, equatorial sea surface temperatures climbed on a scale that is hard to hold in the mind. Oxygen isotope work suggests shallow tropical water rose from somewhere near 70 degrees Fahrenheit toward the high 90s, and by some estimates past 104 degrees, over roughly 800,000 years. That is bathwater warmth spread across an entire tropical ocean. Beyond a point, the water grew too hot for shelled animals to function, and some researchers argue the equatorial seas became a temporary dead band, pushing survivors toward cooler, higher latitudes. Dissolved carbon dioxide does its own harm from inside, seeping into tissues and blood, throwing the body's chemistry off balance. Heat and hypercapnia together are a plausible key. But they do not explain every pattern in the rock. So try the next key. Acidification. The same flood of carbon that warmed the sky also soaked into the sea, and there it turned mildly to acid, the way carbon dioxide sours any glass of water it dissolves into. For animals that built their skeletons from calcium carbonate, this was a slow theft of raw material. Corals, certain sponges, many brachiopods, bryozoans, and the stalked plated echinoderms all pulled their hard parts from seawater chemistry that was quietly turning against them. One count finds that roughly 81% of marine genera with heavy, calcareous skeletons and low respiratory efficiency vanished. Precisely the animals least able to compensate when the water changed. The reef builders felt it most. The rugose corals, reef architects since the Ordovician, and the tabulate corals, builders since the Silurian, both went fully extinct here, and true reefs nearly disappear from the record for millions of years afterward. Acidification is a strong key, yet it too leaves marks it cannot account for on its own. There is a third key, and it smells of rotten eggs. As the seas warmed, they held less oxygen, and vast volumes of the deep ocean slid into anoxia, water with almost no dissolved oxygen at all. Uranium and other redox-sensitive isotopes record this spreading suffocation immediately before and during the worst of the extinction. In those dead layers, sulfate-reducing bacteria thrived, and their waste product is hydrogen sulfide, a gas toxic to almost everything that breathes. The darkest version of this hypothesis has that poisoned water welling up periodically into the shallows and even venting into the air, killing fish and marine reptiles where the two worlds met. On an anoxic seafloor gone sickly grey and black, microbial mats spread where mineralized shellfish once crowded. Anoxia and hydrogen sulfide make a fearsome key, but timing and global reach are hard to prove for every basin. A fourth key is stranger and dimmer, harder to test because the evidence is chemical and indirect. Some researchers propose that volcanic halocarbons and other gases damaged the ozone layer, thinning the shield that filters the sun's ultraviolet light. Malformed fossil pollen grains at some boundary sections are read by a few workers as sunburn on the living world, mutation from radiation reaching ground and surface water unfiltered. It is a real hypothesis, and an honest account has to name it, but it sits among the least settled of the contenders. Hold it lightly. It may have added weight to the balance without ever being the decisive hand. That brings us to the newest key on the ring, cut in a laboratory rather than found in a cliff. In July of 2026, a study by Marquez and Sperling appeared in the Proceedings of the National Academy of Sciences, and it approached the problem from an angle the rock alone cannot show. Instead of reading ancient chemistry, they measured living animals. In tanks, they warmed the water around modern marine invertebrates and recorded exactly how much oxygen each creature burned as the temperature rose. The logic is simple and unforgiving. Warmth speeds up an animal's metabolism, which raises its demand for oxygen at the very moment warmer water holds less oxygen to give. Somewhere in that squeeze, demand outruns supply, and the animal cannot catch its breath. Their experiments centered on brachiopods, the stalked, calcite-shelled filter feeders that had ruled the seafloor for something close to 280 million years. Against them they set bivalves, the clams and their kin. When the model applied warming of roughly 8 to 12 degrees Celsius, about 14 to 22 degrees Fahrenheit, unfolding over thousands of years, the brachiopods hit a wall. Their oxygen demand climbed faster than their bodies could satisfy it. The more metabolically flexible bivalves, by contrast, coped, survived, and later spread into the emptied seafloor to become the dominant shelled animals we still find crowding beaches today. Here at last was a mechanism that explained not just how much died, but who died, and who inherited the ruins. The old body plan was not unlucky. It was, in a warming sea, physiologically outrun. Notice what this key does to the others. It does not shove them off the table, it sits among them. Heat, acid, anoxia, and metabolic failure are not 5 separate stories competing for one throne. They are 5 pressures on the same struggling animal at the same moment. The current view among most researchers treats them as a compounding cascade, a stack of stresses that together crossed a threshold none of them might have crossed alone. Weigh the evidence like 2 hands cupped on a balance. On one side, the direct thermal poisoning of the tropics. On the other, the slow chemical starvation of skeleton builders. The hands never quite come to rest. The relative weight of each mechanism is still actively studied, still shifting with every new core pulled from the ground. If that were the only debate, it would be enough to keep laboratories busy for a generation. But there is a second, deeper question folded underneath it, and it changes the shape of the whole event. Was this one catastrophe, or 2? For a long time, the end-Permian was told as a single blow, one convulsion at the boundary that erased the old world. Then attention turned to an earlier wound. Roughly 9 to 10 million years before the main event near the end of the Middle Permian, the fossil record shows another sharp loss, the Capetanian extinction, sometimes called the end Guadalupian. It has its own likely trigger, a separate and earlier pulse of volcanism, the Siberian Traps in what is now southwestern China. More and more researchers now recognize the Capetanian as a genuine crisis in its own right, not merely a rough patch on the road to the larger dying. If they are correct, the late Permian world absorbed not one great blow, but 2, staggered across millions of years, each with its own volcanic engine. This matters for reading everything that follows. An ecosystem already thinned by an earlier extinction meets the second one weakened, its safety margins spent, its web of relationships already frayed. Whether the 2 events shared any deeper cause, or simply fell one after the other by the accident of where and when the Earth chose to erupt, remains open. It is not settled consensus, it is an active argument, and the honest position is to hold both possibilities in view. There is a third debate, quieter but just as important, and it concerns whether land and sea died together or in turn. Earlier work hinted that the terrestrial collapse recorded so well in the tusked dicynodonts of South Africa's Karoo Basin might have lagged behind the marine one, or perhaps run ahead of it. If the timelines were offset, it would suggest different killers on land and in water. But correlation work through roughly 2019 to 2021, tying rock chemistry to fossil ranges with new precision, now argues that the 2 crises were essentially synchronous. The seas and the continents faltered at very nearly the same moment. Some vertebrate records still show a more gradual, protracted decline that resists any single instant story, and that tension has not fully resolved. Yet the weight has shifted toward one shared catastrophe, striking every environment at once from tropical reef to inland floodplain. Set the three debates side by side and a single picture emerges without any of them being fully closed. The killer was probably not one force but a cascade of them, heat and carbon and acid and suffocation and simple breathlessness, each amplifying the next. The crisis may have come as two volcanic blows rather than one, the emission first and the Siberian Traps second. An already wounded world struck again, and when the larger blow fell, it appears to have fallen everywhere at nearly the same time, sparing no refuge on land or in water. None of this is stated here as final. Every number carries an error bar, every mechanism a rival, every date a margin still being narrowed by sharper radiometric clocks. But whatever the exact weighting of the keys, the lock was turning. The evidence, from ancient isotopes to tanks of living clams, points the same direction even as it argues over the details. The tropics were heating past the tolerance of shelled life. The chemistry of the shallows was souring. The deep water was losing its oxygen and brewing its poison. In the warming, acidifying water, the first great dying was already underway. In the warming, acidifying water, the first great dying was already underway. In the warming, acidifying water, the first great dying was already underway. It began in the sea, quietly, before anything on land seemed to notice. The oceans of the late Permian had been the richest place on this world. Shallow shelves ringed the great C-shaped supercontinent, and those shelves brimmed with armoured, calcite-shelled life. Now the water was turning against the creatures inside it, not with a wave, not with a storm, with warmth, and with a slow loss of breath. You can fix the moment with unusual precision. At a quarry called Meishan in Zhejiang province, a thin layer of dark clay marks the boundary. Geologists set the golden spike there, at the base of a bed labelled 27C. That layer has been dated to roughly 251.9 million years ago. It is not a guess, it is a radiometric measurement, refined over decades of patient work. And in the marine rock just below it, and just above it, you can read the largest catastrophe life has ever survived. The numbers are hard to hold in the mind. Estimates for the sea run from about 90% of species lost to as high as 96%. That range is honest, not sloppy. It shifts depending on which study you read, which fossil group you count, and how you draw the boundary in the rock. But every serious estimate lands in the same terrible neighbourhood. This is the worst of the Big Five mass extinctions, the deepest wound in the entire record of animal life. 9 in 10 is a fair rounding, not a slogan. Picture the shallow seafloor as it had been for hundreds of millions of years. A crowded, clicking, filtering world. Brachiopods anchored in their thousands, tiny valves opening and closing, crinoids swaying on stalks like stone flowers, prozoans building lace across the rock. Now imagine that floor going quiet the way a crowded room slowly empties of breathing. Not all at once. One corner falls silent, then another, then a whole wall of them, until the murmur that had filled the water for ages simply is not there anymore. The killing was not random. That is one of the most haunting things about it. The extinction had a preference, a bias in who it took. Among marine invertebrates, roughly 81% of the genera with heavy chalky skeletons and slow, inefficient breathing were erased. Calcareous sponges, rugose corals, tabulate corals, many brachiopods and bryozoans and echinoderms. These were the animals least able to adjust their inner chemistry when the water heated and soured and lost its oxygen. They had built beautiful mineral armour. In this crisis, that armour became a liability they could not shed. Think about what warming water does to a body that lives inside it. Warm water holds less dissolved oxygen. At the same time, heat pushes an animal's metabolism upward, so it needs more oxygen, not less. The demand climbs while the supply falls. For a slow, heavily shelled brachiopod, there was no way to close that gap. A laboratory study reported in 2026 measured exactly this in living relatives, watching how much oxygen brachiopods and clams actually burn as water warms. The old armoured body plan that had ruled the seafloor for some 280 million years simply could not keep pace. More flexible bivalves could. That difference, small in any single animal, decided who inherited the sea. Among the losses was a creature that had been on Earth almost unimaginably long, the trilobites. Segmented, many-eyed, they had crawled and swum since the Cambrian through roughly 270 million years of history. They had survived earlier disasters, dwindled, clung on in a few last lineages. At the end of the Permian, the last of them vanished. After more than 250 million years, the trilobite eye closed for good. No group of them ever appears in younger rock. They belong entirely to the world before. The reefs went too, and their loss reshaped whole coastlines. Rugose corals and tabulate corals had built reefs since the Ordovician and the Silurian, structures that sheltered countless smaller lives. Both groups went completely extinct at the end of the Permian, and with the reef builders gone, the reefs themselves vanished from the global record for millions of years. Where there had been ridges of living stone ringed by clouds of small swimmers, there was now bare sediment and microbial slime. The corals you might picture on a reef today, the stony scleractinians, are a different, later group. They only rise and spread in the Triassic, long after this. You can read the physical cause in the chemistry of the water itself. Sea surface temperatures near the equator appear to have spiked enormously. Oxygen isotope work suggests a climb from around 70 degrees Fahrenheit to values approaching 97 degrees, and by some estimates past 104, over a stretch of roughly 800,000 years. That is bathwater warmth across the open tropical ocean. Some researchers argue the equatorial seas became so hot that they turned into a temporary dead zone, driving the survivors toward cooler, higher latitudes. The middle of the ocean world, once its richest belt, may have become a place animals fled, and where the water was not too hot, it was too starved of oxygen. Uranium isotopes and other chemical tracers record a rapid expansion of anoxia, of oxygen-depleted water, spreading across the shelves just before and during the worst of the dying. In the most poisoned basins, sulfate-reducing bacteria thrived in the dark, and they exhaled hydrogen sulfide. That gas, the smell of rotten eggs, is toxic to almost all animal life. Models suggest it welled up periodically into shallow water and even into the air above, a faint, deadly tang drifting over a sea that was slowly suffocating. If you had drifted across those shallows near the end, you would have found the shells changing. In healthy times, animals laid down thick, strong calcium carbonate. In acidifying water, that becomes harder and harder to do. The oceans, loaded with carbon dioxide, turned corrosive to the very mineral these creatures were made of. Late shells grow thin, they dissolve at the edges. You can imagine them thinning toward the fragility of a wafer. So delicate they might crumble at a touch, the animal spending its energy just to hold its own body together against the water. For a long time, people believed the land was spared the worst, or that it suffered later, on some separate schedule. That picture has changed. The best terrestrial record of this event lies in the Karoo Basin of South Africa, in thick stacks of river-laid rock that preserve the animals of the late Permian in remarkable detail. And what the Karoo shows is that the land did not escape. Between about 70 and 75% of land vertebrate species disappeared. The great tetrapod fauna that had ruled the continents thinned to a shadow. The Karoo record tells the story in two movements. First, a gradual decline through the latest Permian, as if the ecosystems were already fraying, already losing members quietly across a long span. Then a sharper pulse, a steeper drop right at the boundary itself. Recent work comparing the rock chemistry on land with the marine signal argues that the terrestrial crisis was essentially synchronous with the one at sea. Land and ocean were not two separate tragedies. They were one event, striking a single connected world at more or less the same time. The animals that fell hardest were the dicynodonts, the tusked, beaked plant-eaters that had been among the most successful creatures on Pangea. One genus, dicynodon, was so common in the uppermost Permian of the Karoo that its name defines the assemblage zone, the very slice of time at the end of the period. These were not rare specialists. They were the cattle of their world, abundant across the floodplains, cropping the ferns in herds, and in that thin boundary interval they crash. Their bones grow scarce, then absent. One of the most ordinary sights on late Permian land became, within the span of the crisis, a thing of the past. Consider what was lost among them: Scutosaurus, a heavily armoured parareptile of the Russian north, some 8 to 10 feet long, with a body mass estimated as high as around 2,500 pounds, an animal built like a living boulder. Inostrance via, a saber-toothed gorgonopsian, one of the great predators of the age, sighted at roughly 10 to 14 feet in length, with upper canines as long as your hand. The gorgonopsians as a whole, fierce and mammal-like, went completely extinct at the boundary. No mammal-line predator would reach that apex scale again for a very long time. The top of the food web was decapitated. There were smaller casualties too, and their absence is just as telling. Dicynodon, a little burrowing dicynodont only about 18 inches long, had been one of the most abundant animals in the Karoo. It dug spiral burrows as deep as 5 feet, curling shelters in the earth where it sheltered from heat and drought and raised its young. For much of the Permian, its burrows pockmarked the floodplains like the workings of some tireless gardener. Then it too thins out of the record. The small and the humble died alongside the armoured and the fanged. That is a good place to pause and be honest with you about the numbers, because honesty is part of what makes this bearable to sit with. The death toll figures you hear vary: 90%, 96%, 70%, 75%. They shift by study, by fossil group, by whether you count species or genera, by how completely a given rock section is preserved. No single figure is carved in stone for every lineage on Earth. What does not shift is the shape of the thing. Every method, every basin, every careful count agrees that this was the closest life has ever come to ending. The uncertainty is in the last digits, not in the scale. The tempo is debated as well, and it is worth holding that gently. Some geochemical studies argue the core of the extinction was extraordinarily fast, unfolding across tens of thousands of years, a single sharp blow in the rock. Others, reading the vertebrate and plant records, see a more drawn-out decline, a fraying that ran for hundreds of thousands of years before and after the sharpest signal. In deep time, both can be true at once: a slow slide and then a lurch, a long illness and then a sudden turn. The precise pace is still being sharpened with better dating, and that work continues. There is one more loss from this age that stands entirely alone, and it is easy to overlook because the creatures were small: the insects. In roughly 400 million years of insect history, spanning every other catastrophe the planet has thrown at life, there is exactly one time the insects suffered a true mass extinction. This is it. Research on insect genera finds that about 82.6% of them disappeared at the boundary. No other event in their long, resilient record comes close. The most durable animals on land, the ones that always seem to survive, met their single great reckoning here. To feel what that meant, listen to the world before it happened. A Permian evening had no birdsong, because there were no birds. But it was not silent. It hummed and rasped and clicked with insects, a Paleozoic chorus stitched through the fern thickets, the giant relatives of dragonflies and roaches and lacewings filling the warm dusk with sound. Layered underneath were the low grunt and bellows of the dicynodonts moving through the undergrowth. That was the voice of the late Permian. It was the ordinary music of a living continent, and in the boundary interval much of that chorus falls silent. The insect voices thin, whole families of them, whole modes of living simply stop appearing in the rock above. The evening does not go completely quiet because life is stubborn and some lineages endure. But it grows sparse and strange. If you had stood in a Glossopteris forest at dusk before the crisis, the air would have pressed against your ears with sound. Stand in the same place after, and you would notice the gaps, the missing instruments, the thinned and hollowed music of a world losing its performers. You can trace the same emptying in the plants that made those forests. The Glossopteris trees, the broad-leaved seed ferns that carpeted the cool, boggy lowlands of the southern continents, were the great peat-makers of Pangea. Their fallen leaves and stems had been building the coal beds of the future for ages. Across the boundary, those forests collapse. The peat swamps stop forming, and in the rock, coal itself very nearly disappears for a long stretch afterward. A silence in the record that speaks to how thoroughly the green world was undone. Some markers of that plant collapse are still argued over, and it is worth saying so plainly. At many boundary sections there is a spike of strange microfossils, once read as a global surge of fungi feasting on dead wood, a sign of forests rotting worldwide at once. That reading is now contested. Some researchers think the organism was an alga rather than a fungus, and that the spikes at different sites do not line up neatly at the boundary or across the globe. The collapse of the forests is real. The exact meaning of that one fossil marker is not yet settled, and careful scientists hold it loosely. What is not in doubt is the emptying itself, in the sea and on the land, in the water and in the air, the armoured filterers of the shelves, the reef builders that had raised stone cities, the last of the trilobites, after 250 million years, the tusked herds of the Karoo, the saber-toothed hunters that ranged above them, the little burrowers curled in their spiral tunnels, the insect chorus of the warm evenings. Layer by layer, the living richness of an entire world was drawn down toward almost nothing. It is a strange thing to rest with, the scale of it. Not one region, not one habitat, but the whole connected fabric of life, thinning at once, the sea suffocating and souring, the land baking under a sky hazed with sulfur and ash, drifting from eruptions thousands of miles away, the forests failing, the swamps drying, the coal ceasing to form, and through all of it, that slow arithmetic of loss, the crowded rooms of the seafloor emptying of their breathing, one corner at a time until the murmur was gone. If there is comfort here, and there can be, it lies in the fact that this is a survivor's story. You're able to hear it only because life did not end. Something always held on, in a burrow, in a cooler current, in a body flexible enough to bend when the old armoured ones could not. The end of the Permian took nearly everything. It did not, in the end, take all, and the tempo, however you measure it, whether across 10,000 years or a million, was not fast enough to close the door entirely. Even the most severe crisis in the history of animals was, in that one sense, incomplete. Hold that as the tally settles. Up to 96% of marine species, some 70 to 75% of land vertebrates, about 82.6% of insect genera, the only mass extinction the insects ever knew. Figures that drift by study and by group, yet all pointing the same way, all describing the narrowest passage life has ever squeezed through. The world was not going to look the way it had. The old order, the Paleozoic order, was ending, and what came next would rise from a far smaller stock of survivors. For now the water lay warm and quiet over the drowned shelves, the reefs were bare ridges, the forest stood thinned and failing under a hazy sky. The floodplains, once loud with tusked herds, held only scattered bones and empty burrows. Across the single vast continent and its single vast ocean, the great machinery of life had very nearly run down to stillness, its richness spent, its chorus hushed to a few faint voices in the dusk. You might wonder how anyone counts a dying that finished long before the first dinosaur drew breath. The answer is written in rock, and reading it is slow, patient work. It is closer to detective work than to storytelling. Someone kneels on a hillside with a hand lens and a notebook, and they read the ground the way you might read a ledger, layer by layer, from the bottom up, oldest at the base and youngest near the surface. Each band of stone is a page. Each fossil pressed into it is a name in the record, an animal that was alive when that mud settled. And in a few places on Earth, the pages survive in almost unbroken order. One of those places is the Karoo Basin of South Africa. It is a wide, dry expanse of layered sediment, and it holds one of the most complete records of land life anywhere across this whole catastrophe. Rivers once ran here, laying down mud and silt season after season, burying the bones of whatever died on the floodplain. Stacked up over millions of years, those layers became a tall book of stone, and near the top of the Permian pages something goes wrong with the record. Inside a band of rock barely a few feet thick, roughly 2 of every 3 kinds of land animals simply stop appearing. You can walk the slope in an afternoon. You can lay your palm against the interval where a living world thins out to almost nothing. To feel the strangeness of that, hold the scale in your mind. Millions of years of thriving fill hundreds of feet of layered stone below you. The disappearance itself is compressed into a band you could measure against your own forearm. That is what the extinction looks like from the outside. Not a bang written in fire, but a thinning of names in the rock, a page where the ink begins to run out. The clearest name to follow here belongs to dicynodon. It was a tusked, beaked plant-eater, a dicynodont therapside, and for a long stretch of the late Permian it was one of the most common large animals on the planet. There were so many of them, so reliably, that paleontologists named an entire slice of the rock record after it. They call it the dicynodon assemblage zone, the band of stone defined by the presence of this one abundant animal. When a creature is common enough to name a chapter of Earth's history, its absence is loud, and that is exactly what the diggers find. You trace dicynodon up through the layers, bone after bone, individual after individual, and then, near the top of the Permian, the trail runs out. The last of them lie in the rock, and above that line the beaked skulls are simply gone. You can follow smaller residents the same way. There was Dictodon, a stout little burrowing dicynodont only about 18 inches long, no bigger than a plump house cat. It dug spiral burrows that corkscrewed as deep as 5 feet into the floodplain, shelters where it likely waited out the heat and raised its young. Those burrows fossilized too, twisting casts of stone that record a whole way of life. And through the middle and late Permian, they are everywhere in the Karoo, a signature of an animal that was doing well. Then, in the same fatal interval that record thins as well, the corkscrews grow scarce. The floodplain that had been drilled through, with shelter and family, gives way to something emptier. Reading all this is not as simple as noting where a fossil stops. A last known bone is not the same as a last living animal. A creature can vanish from the rock for the plain reason that no individual happened to die and get buried in the right patch of mud at the right moment. Fossilization is rare and absence can lie. So the detectives who work these hillsides do not trust a single missing name. They walk many sections across the basin, they count thousands of specimens, and they watch for a pattern that repeats no matter where they look. When kind after kind after kind fades out of the same narrow band, in section after section, the coincidence collapses. That is no longer bad luck. That is a world losing its inhabitants. The Karoo tells the story of the land. To read the sea, the trail leads halfway around the planet to a working stone quarry near the village of Meishan, in Zhejiang province, in eastern China. This is the place geologists chose as the world's reference point for the boundary itself, the single agreed spot that marks where the Permian ends and the Triassic begins. And the marker that matters here is almost nothing to look at. It is a thin band of dark clay, only a couple of inches thick, tucked between beds of ordinary limestone. You could cover the whole killing layer with one flat hand and have fingers to spare. Yet inside that little seam of clay, the chemistry of an entire ocean lurches sideways. The carbon signal preserved in the rock swings hard, the kind of jolt you would expect if a vast amount of carbon were dumped into the sea and sky in a geological hurry. Below the clay, the limestone is full of the shelled animals that had ruled the seafloor for hundreds of millions of years. Above it, that armoured, calcite-shelled, slow-breathing world is broken. The most careful radiometric dating published in a high-precision timeline of the extinction pins the base of this boundary interval to about 251.9 million years ago. Think of what that number means for the detective work. A crisis that swept two hemispheres has been squeezed down to a boundary you could hide behind a playing card and dated to a hair inside 250 million years. That precision is newer than you might guess, and it was hard won. For a long time the tools were coarse and the rock only whispered. To sharpen the picture, researchers had to line up the pages from Meishan with the pages from the Karoo and from dozens of other sites, and prove that layers on opposite sides of the world recorded the same moment. That is the quiet heart of this science. Not one dramatic dig, but the patient matching of chemical fingerprints and fossil markers across the planet until the separate records click into the same instant. The matching also relied, for a while, on a fossil that has since become a cautionary tale. In many boundary sections around the world, geologists kept finding a sudden spike of tiny branching microfossils called Reduvia sporonites, packed into the rock right around the crisis. For a time, this was read as a global fungal spike, the fossil ghost of a planet's worth of dead and rotting vegetation, a decay bloom marking the death of the forests. It was treated almost as a bookmark, a convenient stripe you could point to and say, here, this is the horizon. It was a tidy idea, and tidy ideas invite a harder look. The harder look complicated it. Some researchers now argue the organism was not a fungus at all, but an alga, which would tell a very different tale about the conditions it grew in. And when workers compared the spikes site by site, they found they did not always land at precisely the same level, and were not reliably synchronous with the boundary itself. So a marker that once looked global and clean softened into something contested and local. That is not failure. That is the method correcting itself, refusing to let a convenient stripe stand in for proof. In this kind of detective work, a discarded clue can teach as much as a confirmed one. Careful correlation reshaped a bigger question too, one about timing. For years there was a real debate over whether the land died at the same moment as the sea, or whether one lagged behind the other by a long stretch. If the Karoo animals had vanished well before or well after the marine shells at Meishan, that would point toward different killers on land and in water, two crises loosely joined. So the diggers went back to the hillsides with finer tools, better dating, and closer sampling of the chemistry locked in the rock. The newer work, gathered through the late 2010s and into the early 2020s, argues that the terrestrial collapse in places like the Karoo was essentially synchronous with the marine one, land and sea, on the same clock. But even that answer keeps its honest edges. The same detailed vertebrate records suggest the land did not die in a single clean stroke. They show a more drawn-out decline, a gradual thinning through the latest Permian, punctuated by a sharper pulse of loss right at the boundary. So the tempo is still argued over. Some read the rock as a near-instant catastrophe compressed into that thin band. Others read a slower unravelling, a world already fraying for a long time before the final tear. Both sides are looking at the same few feet of stone. They are simply weighing how fast the ink ran out. This is the strange intimacy of it. Everything you know about the largest dying the planet has ever suffered comes from small, quiet things. A band of mudstone in a dry South African basin, a seam of dark clay in a Chinese quarry, no thicker than a stack of a few playing cards, a tusked animal whose last bones mark the end of an age, and a contested microfossil that fooled a generation of readers before it was caught. The catastrophe left no witnesses and no monument. It left only the rock and the patience of the people who learned to read it. And when you follow those thin pages up to the line where the names run out, you arrive at the same silence they did. When the dying finally slowed, it left behind a world scraped nearly bare. When the dying finally slowed, it left behind a world scraped nearly bare. Stand on those early Triassic plains and look outward in any direction. You see red, iron-stained mudstone, sun-baked and cracked, running flat to a hazed horizon. Braided rivers wander across it in shallow, shifting channels. Choked with sediment, they have nowhere to deposit and nothing to hold in place. There are no deep-rooted forests to bind the banks. There is no thick carpet of ferns to slow the runoff. When the rains come, they come hard and brief, and the water sheets off the naked ground, carving new gullies, dumping fresh sand across the old. This is a landscape that cannot keep its own shape. It erodes and heals crookedly and erodes again. Listen, and the first thing you notice is what is missing. For long stretches there is almost nothing to hear. No insect chorus rising and falling in the heat. No dense layered hum of a living floodplain. Just wind moving over open ground and the dry rasp of it against low, sparse vegetation. The quiet here has a shape to it, the way silence has a shape inside an unfurnished house. Sound does not get absorbed by soft living things. It travels too far and comes back too clean, bouncing off bare rock and hard-packed clay, so that a single distant sound, the grunt of an animal, the crack of a drying mudflat, seems to carry across an emptiness far larger than it should. The world has been swept out. The furniture is gone. This is the aftermath of the worst day life has ever known, though calling it a day flatters it. The killing stretched across many thousands of years, and the emptiness it left would outlast anything that caused it. Roughly 9 in 10 marine species were gone. On land, something like 70 to 75% of vertebrate species had vanished from the record. The great tusked herbivores that once moved through Glossopteris forests in herds, the saber-toothed hunters that culled them, the armoured plant-eaters the size of a small car, most of them simply were not there anymore. What remained was a thin cast of survivors, moving through a world that had lost most of its cast members and kept the stage. And onto that emptied stage walked one animal so successful, so overwhelmingly common, that its bones alone can define the age. Its name is Lystrosaurus. If you want to understand the early Triassic, you begin here, with this stout, unlovely, wonderfully ordinary survivor. Picture it standing in the shallows of one of those red rivers. It is not large. Depending on the species, it runs roughly 2 to 3 feet long, with the smaller forms closer to 2 feet, and it weighs on the order of tens of pounds, the heft of a mid-sized dog packed into a barrel, and barrel is the right word. Its body is deep and rounded, its chest broad, its limbs short and set for digging. Its skull is strange, foreshortened and blunt, with the eyes and nostrils shoved high and forward, a face that looks half-finished, as if evolution built it in a hurry from spare parts. In the upper jaw sit 2 short tusks, the badges of its family, the dicynodonts. Behind them, no real teeth at all, just a horny beak cropping the low plants that manage to grow in this scarred ground, grinding them between hardened plates. It is, by any measure of elegance, an unremarkable animal, and that is exactly the point. Lystrosaurus is the textbook example of what paleontologists call a disaster taxon, a survivor that inherits an empty world and floods into it. In the earliest Triassic, in some deposits, it is estimated to have made up roughly 75% of all known land vertebrate individuals. Read that number slowly. Not 75% of the herbivores, not 75% of one family. 3 out of every 4 land animals you might dig up from certain layers, of any kind, predator or prey, large or small, is this one squat, tusked, burrowing plant-eater. There has rarely been anything like it in the history of life on land. An entire living world narrowed down almost to a single face. You can find that face across what had been the whole southern supercontinent. Lystrosaurus fossils turn up in southern Africa, in India, in Antarctica, in Russia, scattered across lands that were once stitched together into Pangea. When those animals were alive, you could have walked, in principle, from one population to another without crossing an ocean, and you would have met the same barrel-chested survivor at nearly every stop. It was one of the great pieces of evidence long ago that the continents had once been joined. The same humble animal, buried on lands now separated by thousands of miles of sea. Watch a group of them cross the flats in the low morning light. They do not move quickly. They plod, heads swinging, short legs working, a loose aggregation of brown bodies flowing across the open ground. From a rise, a herd of them moving together looks like a slow brown tide coming in across the red, a single mass with 100 plodding parts filling the space between one dry channel and the next. There is no rival herd to contest the ground. There is no great predator pacing the herd's edges, waiting to cut one out. There is only the tide of them, and the empty plain, and the heat already beginning to climb. That heat is part of why the world stayed empty so long. The same volcanic warming that had done the killing did not switch off when the dying slowed. The early Triassic was a greenhouse world, and a severe one. In the equatorial oceans, sea surface temperatures had spiked toward the high 90s Fahrenheit, in some reconstructions past 100, hot enough that researchers have argued the tropical seas became a kind of dead band, too warm to hold much complex life, forcing survivors toward the cooler poles. On land, the interior of Pangea had always run to extremes, baking summers and cold, dry winters, because so much of it lay far from any moderating coast. Now, with the greenhouse turned up and the forest gone, those swings grew harsher still. This was not a gentle recovery ward. It was a hot, unstable, punishing place, and it stayed that way for a very long time. Nowhere is the loss written more plainly than in what happened to the forests, and to the record they leave behind. Before the extinction, vast wetlands across Pangea had grown thick with peat, the waterlogged half-rotted plant matter that, buried and compressed across ages, becomes coal. The southern lowlands had been carpeted in Glossopteris, broad-leaved seed ferns standing in cool, boggy floodplains, dropping their leaves into stagnant water year after year, laying down the raw material of future coal seams foot by patient foot. Those swamps were among the great carbon factories of the ancient world, and then, in the rock record, the coal simply stops. Across the Permian-Triassic boundary, coal deposits essentially vanish from the geological record, and they stay vanished for an interval often cited at roughly 20 million years. Paleontologists call it the coal gap. Think about the scale of that silence. 20 million years in which the Earth, so far as the rocks can tell us, laid down almost no coal at all, because the peat-forming forest ecosystems that had covered the wetlands of Pangea had collapsed so completely that there was nothing left to make it. The machinery of the swamp had broken. The trees that fed it were gone, and whatever grew back in their place could not do the same work. For that whole span, the wetlands that should have been dark, wet, and thick with rotting vegetation were instead something thinner and poorer. Low plants, opportunists, the botanical equivalent of weeds spreading over disturbed ground. There is a contested marker in some boundary rocks, a spike of strange microfossils once called a fungal spike, and read as the signature of a world of rotting, dying vegetation, mass death of plants feeding a bloom of decomposers. It is a haunting image, and it may be partly true, but you should hold it loosely. Researchers now argue about what those microfossils even are, whether fungus or alga, and whether the spike lines up precisely with the boundary everywhere or only in places. The honest statement is smaller and still striking. The forests failed, the coal stopped, and the ground stayed thin for ages. That thinness fed back into everything. Without deep forests, the rivers ran wild and unbraided across bare sediment, exactly the red choked channels you have been standing beside. Without rich vegetation, the food available to herbivores was sparse and low to the ground, which favoured small, tough, unfussy croppers like Lystrosaurus over anything large and specialised. Without abundant herbivores of many kinds, the whole pyramid of life that should sit above them, the mid-sized hunters, the great apex predators, had almost nothing to stand on. The emptiness was not one absence, it was a chain of absences, each one making the next harder to fill. Which brings us to one of the strangest and saddest ideas in all of paleontology, a phrase worth sitting with in the dark, dead clade walking. It describes a group of animals that survives the catastrophe, that crosses the boundary still breathing, still reproducing, still leaving fossils, and yet is, in some deep sense, already finished. A lineage living on borrowed time, present but doomed. It walks a while longer through the ruined world, and then it goes, not with a single dramatic blow, but with a slow failure to ever truly recover. Survival, it turns out, is not the same as recovery. Some lineages came through the fire only to gutter out on the far side. You can see the shape of it most clearly in what was missing at the top. Before the extinction, the great predators of the late Permian had been the gorgonopsians, saber-toothed hunters on the mammal side of the family tree, our own distant relatives. The largest of them, in Ostrantovaya, from what is now Russia, stretched perhaps 10 to 14 feet long, carrying upper canines reported up to around 6 inches, driving that bulk, by some estimates, well past 1,000 pounds. It was among the most formidable land hunters of its age, and it, with every other gorgonopsian, is gone at the boundary. The whole group is erased, not diminished, not scattered to the margins, extinct, completely, all of them. And here is the part that should make the emptiness feel real. No mammal line synapsid, no relative of ours, regained apex predator status at anything like that scale for a very long time afterward. The top of the food web on land, the role that in Ostrantsevia had filled, sat vacant. For ages after the catastrophe, there was no great saber-toothed hunter of our lineage stalking the herds of Lystrosaurus across those red plains. The role existed. The stage was set for it. There was simply nothing there to play the part. When the eventual great predators of the Triassic did rise to fill that vacancy, they would come, increasingly, from the other branch, the reptile line that would in time give the world crocodile relatives and further on the dinosaurs. The mammal side, our side, had held the crown through the Permian and lost it, and would not truly wear it again for an almost unimaginable stretch of deep time. So when you look across those Lystrosaurus herds and register that nothing is hunting them at scale, understand what that silence means. It is not peace. It is a wound that has not healed. An ecosystem missing its top is an ecosystem out of balance, and an unbalanced world is a fragile one. The fragility was not a feeling. It was measurable, and it has been measured. In the Karoo Basin of South Africa, where the terrestrial record of this whole disaster is written more completely than almost anywhere on Earth, paleontologists have reconstructed the ancient food webs, the trophic networks of the surviving communities. They build models of who ate whom, how many kinds of animals occupied each role, how energy flowed from the sparse plants up through the herbivores to whatever predators remained. Then they test how those model communities respond to stress, whether they absorb a shock and hold, or whether they cascade, one loss triggering the next into another collapse. The Karoo communities of the earliest Triassic came back unstable. The modelling suggests that for at least 5 million years after the main extinction, these ecosystems remained fragile and extinction-prone, primed to topple again under pressures that a healthy, fully stocked community would have shrugged off. They lack the redundancy that makes a living world resilient. In a rich ecosystem, if one herbivore fails, 3 others fill the gap, and the predators barely notice. In the impoverished early Triassic, there were no spares. Lose a link, and the chain broke, and the breaking spread. Full pre-extinction levels of ecological diversity, the models indicate, did not truly return in the Karoo until the Middle Triassic, millions of years further on. That is the deeper meaning of the empty world. It was not merely that the plains looked bare and sounded quiet, though they did. It was that the invisible architecture of life, the web of relationships that holds an ecosystem upright, had been torn down to a few load-bearing threads, and those threads kept snapping. The world did not just look broken, it was structurally broken, and it stayed structurally broken for longer than most of us can hold in mind. Not every survivor down at the smaller scale was Lystrosaurus. though it can feel that way. Alongside it and before it, the Karoo had been home to other burrowers, small dicynodonts like Diictodon, a modest plant-eater around 18 inches long that dug spiralling burrows as deep as 5 feet into the floodplain, sheltering from the harsh swings of heat and cold, perhaps rearing its young down in the cool dark. Burrowing, that habit of going underground, may be part of why the dicynodont survivors survived at all. A creature that can retreat below the surface can ride out extremes that kill things left standing in the open, the killing heat of the day, the cold of the night, the worst of a world gone unstable. The meek did not exactly inherit the earth, but the small, the stout, the tough, and the underground did rather better than the magnificent. And the magnificent were the ones that had vanished. Think of Scutosaurus, the heavily armoured pareiasaur of the late Permian, 8 to 10 feet long, its body reconstructed at masses running up toward 2,500 pounds, plated in bony armour, plodding through the Permian lowlands like a living boulder. Gone. Think of Dicynodon itself, the tusked, beaked herbivore so abundant in the uppermost Permian of the Karoo that its name was given to an entire zone of rock, the marker of the world that ended. Gone, its disappearance one of the clearest lines in the whole terrestrial record. The animals that had defined the old world, that a visitor would have named first, were precisely the ones the new world did without. What inherited the ground was humbler and lonelier and far less varied. There is a particular loneliness to a low-diversity world that is worth letting yourself feel as you drift. Diversity is not just a number that scientists count. It is texture. It is the difference between a forest full of 100 kinds of calling things and a plain where one animal's grunt carries too far across bare rock. The early Triassic had lost its texture. Walk it for a day, and you would meet the same few faces again and again, the barrel-chested croppers at the water's edge, a handful of survivors filling roles that had once been split among dozens. The richness that makes a landscape feel inexhaustible, that sense that around the next bend there is always something you have not seen, was gone. The world had become knowable in a way no healthy world ever is, and that knowability was a symptom of a wound. The oceans, meanwhile, told the same story in water. The great reef-building corals of the Paleozoic, the rugose and tabulate corals that had raised undersea structures since ages long before this one, had gone fully extinct at the boundary. And with them went the reefs. For millions of years, complex reef ecosystems all but disappear from the global record. A reef gap in the sea to mirror the coal gap on land. The shallow water that had once teemed with armoured, shelled, filter-feeding life lay quieter, draped in places with microbial mats, the slime and scum of a simpler biology, reclaiming ground that complex animals had held for hundreds of millions of years. In the worst-hit basins, the water itself had turned hostile, low in oxygen, and in the foulest zones laced with hydrogen sulfide, the rotten egg poison brewed by bacteria in oxygen-starved depths. Life persisted, but it persisted thin and simple and slow to build anything grand again. Hold the two emptinesses together, the bare red plains under their hot-hazed sky, and the quiet, matted, poisoned shallows, and you have the true portrait of the early Triassic. Not a dramatic wasteland of skeletons and smoke, though there had been smoke enough in the killing, something stranger and calmer, and, in its way, more unsettling. A world that simply carried on with most of itself missing, and did not fill the gaps for age upon age. A world where a single tusked survivor could account for 3 of every 4 land animals, where coal stopped forming, where reefs would not rebuild, where the top of the food web stood vacant and the food webs that remained kept quietly collapsing. A long, low, red pause in the history of life. You might expect such a world to feel like it is about to end. It is not. That is the strange mercy in it. Down among the Lystrosaurus herds, life is not going to surrender. These animals grew fast, matured young, bred hard, and died early, living at a pace tuned to a dangerous world, and in doing so they kept the flame lit. In their spiral burrows and their slow brown tides, in the small tough survivors cropping the sparse red plains, the future was being carried, quietly without ceremony. Nothing out there knew it, nothing could. But the branch that would one day give rise to the ruling reptiles of the Triassic, and beyond them the dinosaurs, and beyond them the birds that still cross your evening sky, was down there somewhere in that thin cast of survivors, breathing the hot air, waiting out the emptiness. So take one long, slow breath of that early Triassic air, dusty and warm and strangely still, and let the scale of the quiet settle over you. The killing was finished. The recovery had barely begun, and would not truly begin in earnest for ages yet. In between lay this, a scraped bare world under a hot sky, ruled by the humble and the stout. Its forests failed, its reefs dissolved, its great predators erased, its silence carrying too far across ground that could not hold its shape. The magnificent old world had not merely died, it had been slow to be replaced, and in that slowness lay the strangest chapter of all, the long-ruled emptiness where almost nothing changed. Come down now to the floor of a red valley, in the first light of a Triassic morning, and find one animal already stirring beneath your feet. You would not see it at first. You would see only the plain, wide and rust-coloured, stretching toward low hills worn soft by wind. The ground here is the shade of dried blood and old brick, iron-stained silt laid down by rivers that flood and vanish. Flood and vanish. Little grows. What grows is low and tough, and somewhere in that emptiness, under a shallow dome of packed earth, a Lystrosaurus is waking. The burrow fits it the way a curled fist fits a coat pocket, snug along every knuckle. The tunnel is not deep. A body length, perhaps a little more, angling down into the cooler dark. Its walls still hold the shape of the animal that dug them, the scrape of small claws, the press of a broad flank turning in its sleep. Down here the brutal swing of the Pangean day is softened. Above, the surface bakes by afternoon and chills by dawn. Below, the earth holds an even, patient temperature, and the animal has learned, in the wordless way of its kind, that this is where a body lasts. It is a stout creature, this one. Barrel-chested, blunt, built like a keg with legs. From snout to stubby tail it runs perhaps 2 to 3 feet, depending on which of its several species you have found, and it weighs on the order of tens of pounds, low and dense and hard to tip. 2 small tusks curve down from its upper jaw, pale as worn bone. Behind them there are no teeth to speak of, only a horny beak, a cropping edge for shearing the toughest stems. It is not fast. It is not clever in any way you would flatter with the word. It is a survivor, and in this thin morning that is the only distinction that matters. Watch it climb. The head pushes up first into the open, blinking against the light. And what light! The sun comes through a sky still faintly hazed, a high, thin veil left over from a wounded world, and it falls across the plain, watered pale as skim milk, without warmth, without colour, a light that only promises heat later. The animal holds there a moment, half out of the ground, nostrils working. It is smelling for danger it will almost certainly not find. Old instincts run longer than the things that shaped them. There is a stillness here you would feel in your chest before you understood it. No bird song, for there are no birds, and will not be for 100 million years and more. No hum of bees, few of the rasping insect choruses that once thickened the Permian dusk. Just wind over open silt, the tick of cooling ground, and the low working breath of the animal itself as it hauls its barrel body fully into the day. If you have ever stood in a desert before sunrise and heard your own pulse in the quiet, you know something of this world. Only this quiet is larger. It covers a continent. The Lystrosaurus does not linger on any of that. It has a route. It sets off across the flat at a plodding, rolling walk, feet splayed, belly low, in no hurry, because hurry belongs to animals with somewhere urgent to be. It is heading toward the green. Green is a generous word for it. In the low ground, where a shrinking channel still holds a thread of water, a fringe of tough vegetation clings on. Low-seed fern regrowth, sprigs of horsetail-like stems, the scrubby pioneers that colonize a ravaged land first. This is a world after the great forests, in the long gap when the coal swamps of the old order had collapsed and nothing yet had risen to replace them at that scale. So the animal grazes what there is. It lowers its beak and shears, methodical, unglamorous, working a patch of stems down to stubble and shuffling 3 steps to the next. There is nothing elegant in it. There is only the steady conversion of a hard landscape into one more day of being alive, and it is not alone. That is the strangest part of this scene, and the part you should hold on to as you drift. Lift your eyes from the one animal at your feet and look across the plain. There, and farther off near the water, and along the base of the hills, more of them. Dozens. In some places, if the fossil beds are read rightly, this single kind of creature made up something like 3/4 of all the land vertebrates alive. 3 out of every 4 backboned bodies on the ground, one animal over and over to the edge of sight. A plain of near-identical stout grazers, plodding, cropping, digging, in a silence broken only by the occasional low grunt as one passes too near another. You are looking at what the aftermath of a catastrophe actually looks like from the inside. Not fire, not drama. Just this. A muted, monotonous abundance. A world so emptied of variety that a single hardy survivor could spread across continents almost unopposed, from what is now southern Africa to India to Antarctica, wandering a supercontinent that scarcely cared to stop it. Stay here with it a while. Let the morning warm. This is a good moment to say, quietly, that if these slow walks through deep time are helping you towards sleep, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Now let the plane settle back into quiet and return to the animal at the water. The channel is lower than it was even a few days ago. You can read the record of its shrinking in the banks, the pale rings where the waterline stood and dropped, like the inside of a slowly emptying bowl. The Lystrosaurus wades into the ankles, if you can call them that, and drinks. Its reflection wobbles in the muddy water, blunt and patient. All around the margin the ground is stitched with the tracks of its own kind. Hundreds of crossings pressed into drying mud, a traffic of thirst going back many mornings. Why this animal, and so few others? Part of the answer lives in the way it grew. Study of the bones tells a story of living fast. Fast growth, early breeding, short lives burned bright and spent quickly. A strategy suited exactly to a world that could turn on you without warning. In stable times, slow and steady wins. In a broken world of droughts and lean years and sudden die-offs, the animal that matures quickly and breeds before disaster finds it is the animal that leaves descendants. The Lystrosaurus was built in its very tempo of living for instability, and part of the answer is the burrow you just watched it leave. To dig is to opt out of the worst of the day. When the afternoon comes and the open ground turns to a griddle, when the thin air offers no shade for 100 miles, the animal that can fold itself underground into cool, still dark simply endures what kills the creatures stranded on the surface. The burrow is armour made of absence. It is a pocket of the old, gentler world, carried down beneath the new harsh one, and the barrel body slides into it as neatly as a hand into a mitten, shaped over years to that exact hand. There is one more mercy in this scene, and it is a strange one. Look around again, slowly, all the way to the hills. Something is missing that would have haunted this same valley only a geological breath before. There are almost no predators. In the world that ended, great saber-toothed hunters had prowled the Permian, gorgonopsians the size of bears, some more than 10 feet long, with upper canines the length of your hand. Every one of them is gone now, wiped from the record at the boundary, and no meat-eater of that mass would take their place at the top for a long, long time. So the plodding grazer crops its stems in a peace its ancestors never knew. The emptiness that erased its rivals also erased the things that hunted it. Loss and refuge, wearing the same grey face. By midday the animal has fed enough. It turns its blunt head back toward home, and you follow the roll of its walk across the flat past others of its kind doing the very same thing, each on its own patient errand, a whole plain of survivors moving through a landscape that asks everything of them and offers almost nothing in return. The heat is climbing now. The pale morning light has burned off to a hard, bright glare, and the far hills swim a little in it. At the mouth of its burrow the Lystrosaurus pauses one last time, as it did at dawn, nostrils working the empty air. Then it lowers itself and goes down, head first into the cool, the light narrowing to a coin behind it, then to nothing, and the tunnel closes around its body snug and complete. Above, the red plain shimmers and holds its breath. The channel drops another hair. The wind moves silt from one low place to another and asks no questions. This was a day. One of thousands, one of millions in the long quiet after the dying, lived out by a small stout animal that wanted nothing more than cool earth, a mouthful of green, and morning. The world had been swept nearly bare, and into that bareness had come not a triumph but a hush, filled edge to edge with a single humble survivor waiting out the age. For millions of years that emptiness held, waiting for something to fill it again. For millions of years that emptiness held, waiting for something to fill it again. For millions of years that emptiness held, waiting for something to fill it again. And then, so slowly that no single day could have shown it to you, the filling began. Not a rush, not a sudden green tide sweeping across the dead plains. Just a faint return of complexity, one thread at a time, in seas that had been scoured almost empty of the life that once crowded them. Picture the shallow shelves of the earliest Triassic, warm, still, oxygen-poor water, lapping over grey mud where reefs used to stand. For a long stretch, almost nothing built anything there. The great reef machinery of the old world had shut down entirely. Let that scale settle over you gently, because it matters for everything that comes after. The recovery of the seas, the slow return to something like their former richness, is estimated by researchers to have taken roughly 5 to 10 million years. Not 5 to 10 years, not 5 to 10 centuries, 5 to 10 million years of patient incremental rebuilding, longer than the entire span our own kind has walked upright, stacked many times over. That is the pace of healing on a wounded planet. Nothing about it was quick, and nothing about it was guaranteed. Before you drift too far into that quiet, let me ask one small thing of you. If these long walks through deep time have become part of how you fall asleep, let the channel know in whatever quiet way suits you. It helps more listeners find their own way here, into the dark and the calm. Now, back to the empty sea, and the first faint signs of life learned to build again. The reefs of the Permian world had been raised by creatures that no longer existed. Rugose corals, solitary and colonial, had been building since the Ordovician, a lineage stretching back hundreds of millions of years. Tabulate corals laying down their honeycombed floors had been at work since the Silurian. Both groups, ancient master builders of the sea, went fully extinct at the end of the Permian. When they vanished, the knowledge of how to make a reef vanished with them. The blueprint was gone, the masons were gone, and so, for millions of years, the record of true reef ecosystems very nearly disappears from the rocks of the world. Think of what a reef actually is, and you feel the loss more clearly. A reef is not one animal. It is a city, a dense stack of built structure, each layer raised on the bones of the layer before. Strip that away and you are left with bare seafloor and open water. The shelter is gone, the nurseries are gone, the 1,000 small niches where smaller creatures hid and fed and bred, all gone at once. An empty shelf is not just missing its corals, it is missing every life those corals had held up. The new reefs, when they finally came, were raised by strangers. A different group of corals, the scleractinians, the stony corals whose descendants still build the reefs of the modern ocean, appear and slowly diversify through the Triassic. They were not the heirs of the old builders. They were something new, taking up an abandoned trade. And they did not step into the role in a single generation. They arrived quietly, spread slowly, and only over long ages did they raise reef structure back toward the scale the world had lost. Hold on to one tactile image as you rest. Imagine reef structure rising again the way sediment settles through still water, grain by grain, each mineral speck drifting down and coming to rest on the one before it. That is how a reef returns after a mass extinction. Not in a burst. In the patient accumulation of countless tiny depositions, a fraction of an inch at a time, layer welded to layer over spans of time the mind cannot really hold. You could have stood on that recovering shell for a whole human lifetime and seen almost no change at all. While the corals were absent, the seafloor still held life, but it was a changed cast. The great winners of the recovery interval were not the animals that had ruled before. And here is one of the quietest, deepest turns in the whole aftermath. A changing of the guard so slow that no creature alive at the time could have known it was happening. For roughly 280 million years, the dominant shelled animals of the seafloor had been the brachiopods. You may never have heard their name, and that itself is part of the tale. Brachiopods look at a glance like clams, two shells hinged filtering food from the water, but they are built on an entirely different plan, an ancient lineage that had carpeted the shallow seas of the Paleozoic in staggering numbers. For nearly 300 million years, if you had scooped up a handful of seafloor life, brachiopods would very likely have been in your palm. They were the default. They were the background hum of the ancient oceans, so common they were almost the definition of the seabed itself. The end-Permian crisis hit them terribly hard, and the recovery did not give them their world back. Instead, the bivalves rose. Bivalves are the true clams, mussels, oysters, and their kin, and they had lived alongside the brachiopods for ages as a quieter presence. After the extinction, that order inverted. The bivalves spread, diversified, and took over the seafloor the brachiopods had held for an eon. From that long recovery onward, it is the bivalves, not the brachiopods, that define the shelled life of the sea, straight through to the mussel beds and oyster reefs of the present day. Why did the clams inherit the sea from creatures that had held it for nearly 300 million years? A study led from Stanford, published in 2026, went looking for the answer not in the field, but in tanks in a laboratory, measuring how much oxygen living brachiopods and clams actually burn as their water warms. The finding was quietly devastating for the old rulers. As the researchers warmed the water, the ancient brachiopod body plan raised its demand for oxygen faster than it could actually supply it. The bivalves, more metabolically flexible, could keep pace. In a world heated by roughly 8 to 12 degrees Fahrenheit over thousands of years, that difference was the difference between surviving and being left behind. So the takeover was not a battle. No brachiopod was hunted down by a clam. It was a slower and more merciless kind of change, a sorting by physiology, a filter of heat and breath and oxygen. The animals that could adjust their metabolism to a warming oxygen-starved sea lived on and spread into the emptied world. The animals that could not simply thinned and were overtaken. An empire that had stood for 280 million years did not fall in fire. It was quietly outlasted. Let that sit with you for a moment, because there is a strange comfort folded inside it. Extinction on this scale is not only a matter of who dies, it is a matter of who is still standing when the world stops burning, and what those survivors slowly become. The recovery was written by the flexible, the tolerant, the modest, Not the mightiest creatures of the old world, but the ones best able to endure a poorer, hotter, thinner version of it. The pattern held for the smallest life as well. Across the ravaged shelves, mats of microbes spread over the mud, thriving in the low oxygen conditions that had killed so much else. In the earliest recovery interval, the seafloor in many places belonged to these simple mats, a return to a much older kind of ocean, as if the sea had briefly slipped backward toward its deep past. Only gradually did the layered complexity return. The burrowers churning the mud, the filter feeders rising off the bottom, the predators moving above them. Each of those tiers came back on its own slow schedule, and the full stack took millions of years to reassemble. Now let your attention rise from the sea to the land, because the land tells an even slower story of recovery. If the oceans needed 5 to 10 million years to rebuild their complexity, some estimates for the full return of terrestrial ecosystems run far longer, as much as 30 million years for forests and coal-forming swamps to regain their old richness. The exact figure depends on how you define recovery, and studies differ, and honest researchers will tell you plainly that the number shifts with the question you ask. But the direction is not in doubt. On land, healing was measured in tens of millions of years. The clearest scar of that terrestrial wound is the one called the coal gap. Through the great forests of the Permian world, dense stands of Glossopteris and their kin had grown in cool, boggy floodplains, dropping their leaves and stems into the water year upon year, laying down the thick peat that time would press into coal. Those forests were carbon factories, burying the dead plant matter of an age, and then, for an interval often cited at around 20 million years after the extinction, coal deposits very nearly vanish from the rocks of the world. Sit with what that gap really means. It is not merely that the trees died. It is that the entire machinery for building coal, the whole ecosystem of swamp forest and slow decay and deep peat, stopped functioning across the planet and stayed stopped for a span longer than the age of many mountain ranges. 20 million years with no significant coal laid down. The forests that had carpeted southern Pangea in cool green were simply not there to fall into the bogs, because for a very long time the bogs themselves and the great forest that fed them did not return. In the earliest Triassic, the land was a threadbare place. Red, sediment-choked river plains stretched under a hazy sky, thinly covered by low plants, easily stripped by drought and flood. The rivers themselves changed character, braiding across bare ground where once they had wound through rooted forest. Without deep root networks to bind the soil, the land bled sediment into every channel. You could have walked for a very long way across that early Triassic ground and seen little standing higher than your knee. And moving across that thin red country in astonishing numbers was a single stout survivor, Lystrosaurus. A barrel-chested, tusked, plant-eating dicynodont, most forms only about 2 to 3 feet long, weighing on the order of tens of pounds, built low and heavy for digging and enduring. In the earliest Triassic, this one humble creature became so overwhelmingly common that it is estimated to have made up something like 3/4 of all known land vertebrate individuals for a stretch of time. 3 out of every 4 bodies on the land, a single kind of animal. It is the textbook example of what paleontologists call a disaster taxon, a survivor that floods an emptied world precisely because so little else remains to compete with it or to eat it. There is a strange loneliness in that image, and a strange hope too. Imagine a floodplain at dusk in that early recovery world. No dawn chorus of birds, for birds are still tens of millions of years from existing. No familiar insect drone. Just the low grunts and shuffling of stout Lystrosaurus, moving between their burrows, cropping the sparse growth, wandering across a landscape still scarred by the dying. For a long time, that was much of what the land had to show. A quiet, low, patient animal, waiting out the millions of years until the world grew rich enough to hold more. Here is a truth the recovery teaches without ever raising its voice. An emptied world is not filled all at once, and it is not filled by triumph, it is filled by endurance. The survivors were not conquerors striding into a promised land. They were the tolerant and the tough, holding on through conditions that would have killed almost anything grander, and slowly over ages passing that held ground onto descendants that could do a little more with it. Recovery is not a leap. It is a long, uneven, stubborn refusal to end. The recovering communities were fragile for a long time after the worst had passed. Food web modelling of the Karoo Basin ecosystems in southern Africa suggests that the surviving communities remained unstable, prone to further collapse, for at least 5 million years after the main event. The web of who ate whom had been torn so badly that it could not yet hold steady. A small disturbance that a healthy ecosystem would have absorbed could still, in those early recovery ages, send tremors through the whole structure. The pre-extinction levels of ecological diversity by this work did not truly return until the Middle Triassic, long after the boundary itself. This is the part of the tale that patience rewards, because while Lystrosaurus trudged across its thin red plains and the seas slowly relearned how to build, something else was quietly stirring in the recovering world. The great predators of the old order were gone and would not return in the same form. The saber-toothed gorgonopsians, animals like Inostrancevia, some of them 10 to 14 feet long with upper canines reported up to about 6 inches, had gone fully extinct at the boundary. No mammal-line predator would reclaim apex status at that scale for a very long time. Their empty throne was not refilled by their own kind. It was left open, and into that open space, into the gaps left by the vanished giants of the synapsid world, a different lineage began very quietly to move: the archosaurs. In the recovering Triassic, the first small members of this group appear, modest animals at first, nothing like the rulers they would eventually produce, but the archosaurs are the branch of the reptile family that leads in time to the crocodile line on one side and on the other to the dinosaurs. The empty world, slowly greening, slowly cooling from its fever, was making room for them. It is worth pausing on how undramatic this was at the time. There was no moment when the first archosaur stepped forward and the age of dinosaurs began. There was only a recovering world with unclaimed roles in it, and a group of small, capable animals gradually spreading into those roles as the ecosystems around them grew rich enough to support more kinds of life. The stage was not handed to them. It was cleared by catastrophe, and then, across millions of patient years, slowly furnished again by recovery, until at last there was enough of a world for new rulers to inherit. Let yourself feel how much time this took. The dinosaurs proper are still far in the future during this recovery interval, tens of millions of years away from their earliest true forms, and much further still from the giants most people picture. What the recovery built was not dinosaurs. It was the conditions in which dinosaurs would one day become possible: a stabilizing climate, returning forests, rebuilt food webs with room in them, reassembled seas. The archosaurs were simply the lineage in the right place, with the right flexibility, as that world slowly came back to life. Return for a moment to the greening of the land itself, because it is the gentlest image the whole recovery has to offer. Over those long Triassic ages, plant life crept back across the bare red plains. First the low, hardy, opportunistic growers, then, over immense spans, taller and more complex vegetation, and eventually, far down the line, forests once more. If you could watch it from far above and speed the millions of years into a single slow breath, you would see green soaking back into the land the way colour returns to washed cloth, faint at first, then deepening, spreading from the wet lowlands outward until the world wore living colour again. That greening was not even, and it was not swift, and it did not erase the memory of the dying written in the rocks. The scars remained. The coal gap stayed empty for its long 20 million years before true peat forests rebuilt. The reefs took their 5 to 10 million years, and more to rise again from bare shelf. The full richness of the forests, by some estimates, needed 30 million years to return. But return it did, thread by thread, tier by tier, in the slow accumulation that healing always is on a planet this size. There is one more honest thing to hold as you rest. The end-Permian catastrophe was so total that the world which grew back was not a copy of the world that had been lost. The old rulers did not simply resume their reign once conditions improved. The brachiopods never again dominated the seafloor as they had. The bivalves held it. The great synapsid predators never reclaimed their scale. The archosaurs began their long rise. The ancient corals never came back. New stony corals built the reefs of every ocean since. A mass extinction does not press pause on the living world. It clears it, and whatever grows back grows into a genuinely different shape, carrying forward only the survivors and whatever those survivors could slowly become. And so the emptiness that had held for so long did not end with a triumphant leap, and it did not end on any single morning you could name. It ended the way a wound closes, unevenly, slowly, from many small points at once. Corals rising grain by grain on the bare shelves. Clams spreading across the mud the brachiopods had ruled for an eon. Microbial mats giving way, tier by tier, to a fuller sea. And on the land, green soaking back into red plains across ages beyond easy imagining, until the world that had nearly died held enough life again to carry something new. That is the true shape of recovery, and it is a shape worth carrying into sleep. Not rescue, not rebirth in a flash, just endurance and time and the patient accumulation of small living things doing what living things do, filling every space that opens to them for as long as it takes. The planet did not hurry because the planet never hurries. It simply kept, across millions of years, adding one more thread to the weave until the empty world was empty no longer. Stand now on one of those red river plains a few million years after the dying, and let your eye travel across it slowly. For a long time this ground was nearly bare. Sediment ran loose across it, unbound by roots, and every rainy season the channels shifted and choked and started over. But look closer at the low, damp margins where water lingers longest. Something green has begun to return. Not a forest, not yet. Only patches, small and scattered, ferns and low ground cover creeping out from the wettest hollows, the way colour seeps into cold fingers as they slowly warm. You could walk a long while between one green patch and the next. The recovery on land was not swift, and no honest account pretends it was. Some researchers estimate that full ecological complexity, the deep and layered forest and swamp systems that had covered the old world, took as long as 30 million years to rebuild. 30 million years! Longer than the entire age of many mountain ranges, you know. The coal seams that had once formed in vast boggy lowlands simply stopped forming, and that absence, the coal gap, stretches through roughly 20 million years of rock with almost no trace of thriving peat forest at all. So the greening you are watching is patient work. It comes in inches. Kneel at the edge of one of these returning fern beds and press your palm flat against it. The mat gives, under your hand, soft and yielding and cool, damp as a wrung sponge left on a windowsill. Beneath the fronds the soil is beginning to hold together again, threaded with fine roots, no longer just loose red grit washing downhill. Each small stand of plants slows the water a little. Each slowing lets the next seed settle. That is how a world knits itself back, one held handful of ground at a time. The air here still carries the memory of the long drought. Away from these green margins the plains run dry and open, and the wind lifts fine red dust that hazes the low sun. Move through this landscape and you meet, again and again, the same stout animal. Barrel-bodied, tusked, no longer than 2 or 3 feet, plodding between the waterholes with a beaked, grazing patience, Lystrosaurus. For a stretch of the early Triassic, this single burrowing plant-eater is thought to have made up roughly 3/4 of all known land vertebrate individuals. 3 out of every 4 bodies on the ground, one kind of animal. You could travel for days and see little else with a backbone. There is a strange loneliness to that abundance. A crowd made of one face. The great predators that had ruled before were simply gone. The saber-toothed gorgonopsians, some of them 10 to 14 feet long with upper canines near 6 inches, had vanished entirely at the boundary, and no mammal line hunter would reclaim that size and rank for a very long time. The armoured pareiasaurs like Scutosaurus, animals that had carried well over 1,000 pounds of bone and bulk across these same basins, were gone too. What remained was small, low, and hardy. The meek genuinely inheriting a scoured earth? Turn now from the land and go down to the shore, because the sea is telling its own slow version of the same story, and it is worth hearing before you drift. Wade out into the warm shallows over what was, for millions of years, a barren floor. The old reef builders are absent here. The rugose corals, reef makers since the Ordovician, and the tabulate corals, builders since the Silurian, both went fully extinct at the end of the Permian. For a long span afterward, reefs essentially disappear from the rock record of the whole planet. The shallow seafloor that had been a cathedral of shell and lime for hundreds of millions of years lay flat and quiet, draped in places with microbial films where mineralized life had once crowded thick. And then, in the Triassic warmth, something new begins to frame itself against the current. A different kind of coral, the scleractinians, the ancestors of the reef builders that still ring warm coast today, starts to take hold and diversify. Hover over one of these young thickets and watch how it grows. Not as a finished reef, nothing so grand, only a low crust of new skeleton reaching upward in fine ridges and branches. It builds the way frost builds across a cold pane through a long night, spreading in slow crystalline fingers, furring the bare surface a little further each season until a structure stands where there was only smoothness before. These first thickets are the earliest scaffolding of true reefs the world has held in millions of years. Small fish and soft-swimming things begin to find shelter in the gaps. Where the water passes through the branches it slows, the way it slowed among the returning ferns on land, and in that slowing more life can settle and hold. The parallel is quiet and exact. On land and under the waves alike, recovery begins with something that breaks the flow. A fern mat, a coral crust, a first fixed point around which a community can gather. Wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice, follow or subscribe and let the tide of this slow world carry you. Marine recovery ran faster than the land, though faster is a gentle word for it. Researchers generally put the return of comparable ecological complexity in the oceans at roughly 5 to 10 million years. Still an unimaginable patience by any human measure, yet perhaps a third of the time the forest needed. The sea, it seems, could rebuild its layered communities sooner than the land could regrow its deep swamps and canopies. Both timescales ask the same thing of you. They ask you to feel how vast a wound this was, that healing it took spans longer than most creatures you can name have existed. Listen now, because the soundscape is changing, and change here is measured in the faintest increments. Stand again on the shore at dusk. In the worst years after the dying, a coastline like this was nearly silent, only wind and water and the dry hiss of blowing grit. There was little to hum, little to call, little to move through the shallows and stir them. Now, slowly, the quiet is filling, the click and rasp of small living things returning to the water, the low grunt of a Lystrosaurus somewhere back among the fern patches, settling into its burrow for the night, the wet shift of shallow water over the young coral. It is not yet a chorus. It is far, far short of the dense living richness the Permian world had held before the collapse. But it is no longer emptiness. It is a hum beginning to gather, note by note, out of a very long silence. Feel the temperature of this recovering world against your skin. It is still warm, warmer than the Earth you know, the heat of the great warming only slowly bleeding away over ages. The shallows over the coral are bath-water warm at midday. But the killing extremes are easing. The equatorial seas that had spiked to lethal heat, oxygen-starved and hostile, are cooling back towards something life can hold in. The sulfur haze that once drifted from eruptions thousands of miles away has thinned, and the sky over these plains runs clearer, a paler and more ordinary blue above the red ground. There is a texture to standing inside a recovery like this. Nothing announces itself. No single dawn arrives when the world is suddenly whole again. Instead, there are 10,000 quiet mornings, each almost identical to the last, each carrying a fraction more green than the one before. The fern beds widen by a handspan a lifetime, the coral crusts thicken by a fingernail a season. Communities that food web models suggest stayed fragile and prone to further collapse for at least 5 million years. Slowly steady themselves. You would have to stand here across a span longer than you can truly imagine to watch the change with your own eyes. But it is happening, under your feet and beneath the warm water, all the time, and in that patient thickening of life, something opens, not loudly, a space clears. The old rulers are gone and their thrones stand empty, and into a warming, greening, quietly filling world, room appears for new kinds of animals to grow into the gaps the dying left behind. The largest niches, the roles once held by the tusked giants and the saber-toothed hunters, wait unclaimed. A door stands ajar, and the light of the Triassic falls through it onto ground soft enough at last to build a lineage upon. You can feel the poise of it if you stand very still here in the warm dusk, among the spreading ferns and the first faint reefs, in a world learning how to be full again. Everything that had crowded this earth before was reduced to a handful of hardy survivors. Everything that would one day tower over it had not yet arrived. Between those two conditions lies this long green, unhurried in between, this recovering world you're standing inside now, breathing its warm and dusty air, listening to its quiet hum rise. The stage was nearly bare, the lights were coming up, and in that slow greening the first small archosaurs took their earliest steps toward everything that would follow. And in that slow greening the first small archosaurs took their earliest steps toward everything that would follow. And in that slow greening the first small archosaurs took their earliest steps toward everything that would follow. They were not the giants yet. They were slight, quick-footed reptiles moving through fern shade, no larger than a modern dog, easy to overlook. You would have knelt to see one clearly, but their ankles hinged in a new way, their strides ran long and efficient, and the emptied world had left them room. Around them, the land was still healing. It had been healing for a very long time. Rise with me now, slowly, away from that Triassic floodplain. Let the ferns blur beneath you. Let the small archosaur become a fleck, then nothing, as the river braids widen into a pale ribbon, and the ribbon becomes one thread, among many across a drying plain. Think of how long this took. The seas had lost almost everything, and the seas were slow to answer. Reefs, once vast limestone cities built by rugose and tabulate corals, had gone silent across the whole planet. Those old reef builders never returned, they were simply gone. In their place, after millions of empty years, a new kind of coral, the scleractinians, began to raise the first fragile new reefs of the Triassic. But complexity like the old world had known took time. Marine ecosystems needed something on the order of 5 to 10 million years to rebuild a comparable richness, and even the estimate shifts from study to study. On land, it was slower still. The forest that had covered Pangea, the broad-leaved Glossopteris woods that fed the coal swamps, had collapsed so completely that coal itself nearly vanishes from the rock for roughly 20 million years afterward. Geologists call that quiet interval the coal gap. It is a silence you can read in stone. For those long spans, the peat-forming forests did not come back because the trees that made them were gone and the soils that held them had washed away. Some researchers argue the fullest terrestrial recovery, forests and swamps woven back into their old complexity, took as long as 30 million years. 30 million years. Hold that number gently, the way you would hold something warm. It is longer than the whole age of many mountain ranges, you know. And through all of it, the world kept turning, patient and unbothered, healing at a pace no single life could ever witness. Lift higher now. Let the plains shrink. Let the coastlines curl inward. Down in the Karoo, in the rocks of southern Africa, the recovering communities stayed fragile for a long while. Food webs modelled from those layers suggest the surviving animals lived in unstable arrangements, prone to collapsing again for at least 5 million years after the worst had passed. Diversity like the old Permian world would not truly return until the middle Triassic. Recovery was not a single dawn. It was a long, uneven grey morning, with false starts and quiet setbacks, stretched thin across an unimaginable span. Rise further. The single ocean, Panthalassa, spreads out below you as one unbroken blue, and the great C-shaped bulk of Pangea narrows toward the horizon. From here you cannot see the burrowing herbivores, or the small archosaurs, or the new corals feeling their way upward in warm shallow water. You can only see the shape of a world putting itself back together, one slow layer at a time, and so gather the whole of it gently without counting. There was a world that was full. Then there was a wound so deep that life came within a breath of ending. Then there was a long silence, emptier and quieter than anything before or since. And then, without hurry and without any promise, life returned. Not the same life, never the same, but life, patient and stubborn, filling the spaces the dying had left behind. That is the door the great dying opened, though no creature at the time could have known it. The old rulers were gone, tusked giants, the saber-toothed hunters, the armoured plant-eaters, all cleared away. Into that opened world walked the ancestors of the dinosaurs, small and unremarkable at first, inheriting a planet remade. Everything that would come after, the long reins and the towering forms and the footprints pressed into ancient mud, traces back through that narrow surviving thread. Rise until the continents draw together beneath you, until all of Pangea shrinks to something you could cover with a single thumbprint held at arm's length. From up here the catastrophe has no sound. The eruptions are stilled. The dead seas are calm. The whole crisis, the longest and worst that life has ever known, softens into a single thin band in the rock, a line you could trace with one fingertip. Let that be enough for tonight. You do not need to hold the numbers anymore. Let them settle out of your hands like sediment drifting to a quiet seafloor. The reefs rebuilt themselves. The forests came back. The small, quick reptiles grew in time into the animals that would fill your imagination. None of it needed to be remembered by anyone to happen. It simply happened, slowly, across a depth of time so vast that a human life beside it is barely a flicker. And there is something restful in that. The world has ended before, in nearly every way that matters, and the world went on. It greened again. It filled again. Whatever the rocks remember, they remember it calmly now, layer resting on patient layer, the worst day sealed quietly beneath all the days that followed. Drift a little higher. Let the blue soften. Let the single ocean go pale at the edges. The heat is gone. The toxic seas are only stone now, folded into cliffs and quarries, read one thin line at a time by patient hands far in the future. All of that is elsewhere, and none of it needs you tonight. Feel the pullback slow. The planet turns beneath you, unhurried, a small blue-green thing carrying the long memory of its own recovery. Deep time thins from 30 million years, from 10, down and down, until all of it seems to gather into a single held breath, quiet and complete. Let your own breathing settle to match it, slow, even, unforced. There is nothing left tonight to hold. The dying is long over, the healing is long done. The forest you know grew from that patience, and so, in a way, did you. Take one last easy breath and let the world grow small and warm below you, the continents drawing in, the seas going still, the long recovery folded gently into the rock where it will rest for as long as there is earth to hold it. You have travelled a very long way tonight, across more time than any mind can truly cross. You can put it down now. The small archosaurs are safe in their ferns. The new reefs are rising in their warm shallow seas. The forests are coming back slowly in their own unhurried time, and the world, having survived the worst it ever faced, turns on beneath you, quiet and green and patient, needing nothing more from you than rest. Sleep well tonight, traveller. Good night.